Picture a clock not just ticking, but its very metal softening, its numbers dripping like wax into a puddle of impossible time. Or witness the final, violent moments of a star, its immense bulk collapsing inward, not just into a black hole, but into a gateway to everything that has ever been or could ever be. These aren't just scenes from a science fiction film. They are glimpses into a question that has haunted humanity's greatest minds for centuries. What if time, the steady, unyielding river we all float upon, is not so steady after all? What if it could be crossed, reversed, or perhaps even created? Today, we're not just asking that question. We are reaching back to the very beginning of everything to hunt for an answer. We are searching for evidence of the universe's very first instance of time travel. Think about that for a moment. The first time travel, not a machine built in a lab, not a mystical portal discovered by accident, but a fundamental event woven into the birth of reality itself. A moment so profound that it might have set the rules for causality as we know it, a single glitch or feature in the cosmic code that could explain why the universe looks the way it does. This is the ultimate cosmic detective story, a puzzle whose pieces are scattered across 14 billion years of history, from the fiery first instant of the Big Bang to the cold, dark fate that may await us all. And the clues don't just come from physics. We'll be drawing from the wildest ideas in theoretical cosmology, the profound questions of philosophy, and the visionary dreams of science fiction. Because when you're investigating the impossible, you need to look everywhere. Over the course of this journey, we will explore 30 of the most incredible, mind-bending theories ever proposed about this primordial event. We will venture into realms where gravity becomes so strong that it twists time into a loop, where entire universes are born from a journey backwards, and where the very first cause might also be the final effect. This is an invitation to step into the unknown with us, to let your imagination run wild while keeping one foot firmly planted in the cutting edge of modern science. We're about to unravel the mysteries of time itself, starting from a point before time, as we understand it, even existed. So, get ready to question everything you think you know about past, present, and future, because the story of the first time traveler is the story of reality's deepest secret. Our journey into the cosmos's deepest secret begins not with a bang, but with a rebound. The first theory proposes that the universe's genesis was the ultimate act of temporal defiance. Imagine the entire cosmos not as a one-time explosion from nothing, but as a single heartbeat in an infinite series. This is the concept of the Big Bounce, a cyclic model where our expanding universe is merely the aftermath of a previous universe's collapse. Instead of a definitive beginning, the Big Bang was a moment of tremendous recoil. In this view, the event we call the beginning was actually a turnaround, a point where the arrow of time, which had been pointing toward a final, all-encompassing crush, a big crunch, suddenly reversed its direction. Think of it like a cosmic echo. When a sound wave hits a barrier, it bounces back, carrying some of its original information with it. In the same way, the theory suggests that as the previous universe contracted into an ultra-dense, ultra-hot state, it didn't simply vanish into a singularity of nothingness. Instead, the fundamental laws of physics, perhaps guided by quantum mechanics we don't yet fully understand, allowed for a smooth transition. The collapse reached a critical point and then rebounded, expanding outward to become what we now observe as our own universe. This means the information, the fundamental blueprints of particles, forces, and perhaps even the structure of space-time itself, from that prior cosmos didn't just cease to exist. It traveled across the bounce, effectively moving from the far future of that dead universe into the earliest moments of our own. This is where time travel enters the picture in its most profound form. If the information from the previous cycle survived the transition, then the Big Bang becomes the universe's first, and most consequential time machine. The history, the laws, even the potential for life from a cosmos that existed trillions of years before our own could have been sent back in time to seed the conditions for everything we see today. The cosmic microwave background radiation, that faint afterglow of the Big Bang that fills all of space, might not just be a relic of our birth. It could be a palimpsest, a layered message containing faint imprints of an earlier existence. This idea transforms the Big Bang from a creation event into a transformation event, a cosmic reset that nevertheless carries forward a memory. It suggests that our universe is not a lonely, isolated phenomenon, but part of an endless, breathing cycle of death and rebirth, where the end of one story is literally the beginning of the next. But how could we ever hope to find evidence for such an unimaginable event? The search for the Big Bounce leads us to the oldest light in the universe, a fossilized echo from its infancy known as the cosmic microwave background, or CMB. This faint, cold radiation permeates all of space, a uniform glow that is the redshifted remnant of the universe's hot, dense youth. For cosmologists, the CMB is like a cosmic fingerprint, and within its subtle, almost imperceptible variations in temperature, they are hunting for scars that might tell a story from before our time. The idea is that the violent transition of the bounce, the moment of infinite density, and the subsequent recoil would have sent powerful gravitational waves rippling through the fabric of the newborn universe. These primordial ripples would have left a distinct pattern, a specific type of polarization, imprinted on the CMB. Finding this specific signature, often referred to as the B-mode polarization, would be like discovering a manufacturing stamp on reality itself, a mark of the process that brought our universe into being. The challenge, however, is monumental. The signal they are looking for is incredibly faint, buried under noise from our own galaxy and distortions from later cosmic events. It's akin to trying to hear a single, specific whisper in a crowded stadium roaring with noise. Sophisticated telescopes located at the driest, coldest places on Earth, like the South Pole, and instruments mounted on high-altitude balloons, are tasked with this delicate work. They are meticulously mapping the CMB's polarization, filtering out the cosmic static in the hope of revealing the ghostly imprint of the bounce. A detection would not merely confirm a theory, it would revolutionize our understanding of existence. It would provide the first tangible evidence that our universe is part of a much grander, cyclical cosmos, that there was a before the Big Bang, and that information can, in a sense, travel across the ultimate temporal barrier. Yet, absence of evidence is not evidence of absence. The failure to find these specific patterns so far doesn't kill the theory. It simply forces scientists to refine their models. Perhaps the bounce was smoother than predicted, leaving a fainter mark, or maybe the imprints are of a nature we haven't yet learned to recognize. The very act of searching pushes the boundaries of our technology and our theoretical models, forcing us to ask deeper questions about the nature of time and causality at the most extreme energies. This quest transforms the cosmic microwave background from a simple snapshot of the universe's baby picture into a potential palimpsest, a canvas on which the final moments of a previous cosmic cycle might have been etched, waiting eons for a species curious enough to learn how to read it. Moving from the vast cycles of the Big Bounce, we zoom in to an almost incomprehensibly brief moment in our universe's own history. This brings us to a theory that tackles one of the most puzzling features of our cosmos, its profound uniformity. Look up at the night sky in any direction, and the universe appears remarkably similar. The temperature of the cosmic microwave background is the same everywhere to within a tiny, tiny fraction of a degree. This presents a monumental problem because according to the standard Big Bang model, these regions of space should never have had time to communicate with each other. They were simply too far apart for light, or any influence to have traveled between them to even out their temperature. It's as if you walked into a vast, crowded room where every single person, without having spoken, was wearing the exact same outfit down to the smallest detail. How could such perfect coordination have occurred? The leading solution is a theory known as cosmic inflation. It proposes that a fraction of a second after the beginning, perhaps around 10 to the power of negative 36 seconds, the universe underwent a growth spurt of staggering proportions. For an unimaginably short instant, space itself expanded faster than the speed of light, blowing up a subatomic speck of primeval universe to something much larger than the entire observable cosmos we see today. This explosive stretching would have smoothed out any initial wrinkles, ironing the universe flat and making its temperature uniform, just as inflating a balloon smooths out its crumpled surface. But within this incredible mechanism of inflation lies a possibility even more bizarre, a potential form of time travel woven into the fabric of the universe's rapid expansion. The driving force behind inflation is thought to be a mysterious energy field, often called the inflaton field. The energy density of this field during that brief period was unlike anything we can create or even fully comprehend. In such an extreme environment, the very rules of spacetime are pushed to their limits. According to Einstein's general relativity, energy warps spacetime. The immense energy of the inflationary field wouldn't just push space apart. It would have twisted and contorted the newborn fabric of reality in wild, unpredictable ways. Under these conditions, the formation of microscopic wormholes, theoretical tunnels connecting different points in spacetime, is not just possible, but perhaps even probable. These wouldn't be the stable, spaceship-sized wormholes of science fiction. They would be quantum-scale fluctuations, bubbling in and out of existence like foam on a turbulent ocean. But here's where the time travel element emerges. In the complex geometry of general relativity, a wormhole can easily connect not just two different places, but two different times. A particle could enter one end of a microscopic wormhole and emerge an instant before it entered, effectively taking a brief journey into its own immediate past. Now, imagine this happening not just once, but trillions upon trillions of times across the entire inflating universe. This chaotic web of transient time loops could have created a hidden network of causal connection. Even though regions of space were being blown apart faster than light, they might have remained in contact through these brief, time-bending shortcuts. Information about temperature and density could have been exchanged not just across space, but backwards through tiny intervals of time, allowing the universe to achieve its uniform state. The stunning homogeneity we observe today, which seems to defy causality, might actually be the fossilized evidence of a fleeting epoch when the universe was a seething cauldron of microscopic time travel. The inflaton field, in its drive to expand the cosmos, may have inadvertently peppered it with temporary time machines that orchestrated the large-scale structure of everything we see. This idea transforms inflation from a simple smoothing mechanism into a process that potentially used violations of our everyday understanding of time to set the stage for the universe we inhabit. While inflation provides a mechanism for temporary, microscopic time loops, another theory suggests the early universe may have forged far more substantial and enduring temporal passageways. This brings us to the concept of primordial wormholes, often called Einstein-Rosen bridges. To grasp this idea, we need to revisit the very first instance after the Big Bang, when the entire cosmos was compressed into an inconceivably hot, dense state. In this primordial soup, the fabric of spacetime wouldn't have been smooth and calm. Instead, due to the fierce energies and wild quantum fluctuations, it would have been a seething, frothing chaos, often described by physicists as quantum foam. At this microscopic scale, space and time would lose all semblance of stability. Tiny tunnels, or wormholes, would be constantly bubbling into and out of existence, connecting different points in this foamy spacetime in a random, fleeting dance. These aren't the grand, stable structures you might see in films, but rather ephemeral quantum phenomena. However, the theory proposes that some of these nascent wormholes, born in the fury of the universe's birth, could have been stretched and potentially stabilized by the subsequent rapid expansion of the cosmos, particularly during the inflationary epoch we just discussed. As the universe blew up like a balloon, a microscopic wormhole connecting two points that were initially right next to each other could have been stretched to an astronomical scale. One end of the tunnel might have been carried to one side of the universe, while the other end was propelled to the opposite side. And here is the crucial twist from Einstein's theory of general relativity. A wormhole doesn't just connect two locations in space. Because space and time are intrinsically linked, a wormhole naturally connects 2 points in spacetime. If one end of the wormhole is then moved relative to the other, for example, by being dragged at a significant fraction of the speed of light, time dilation effects would cause time to pass at different rates for each mouth of the tunnel. The result is a bridge through time. An object entering the mouth that had been moving quickly would find itself emerging from the other, relatively stationary mouth at a point in time before it even entered. This creates a closed time-like curve, a path through the universe that allows travel into the past. But there's a monumental catch to this idea: stability. A wormhole born from the quantum foam would be incredibly unstable. According to our current understanding, it would pinch shut or collapse the instant anything, even a single photon of light, tried to pass through it. The gravitational forces involved would simply be too great. To keep such a tunnel open and traversable, you would need a very strange kind of material to line its throat, something known as exotic matter. Exotic matter isn't just rare or unknown. It theoretically possesses a property that defies everyday experience: negative energy density, or negative pressure. This bizarre substance would have a repulsive gravitational effect, effectively propping the wormhole's throat open against the crushing force of its own gravity. While this sounds like pure fantasy, such exotic quantum states are not entirely ruled out by physics. The Casimir effect, a well-demonstrated quantum phenomenon, shows that regions of space can indeed have negative energy densities. This leads to a fascinating possibility. In the extreme energy conditions of the very early universe, during the Planck era, when all fundamental forces were unified, vast quantities of this exotic matter might have naturally existed. It could have been a fundamental component of the quantum foam itself. Under those unique circumstances, it's conceivable that not all primordial wormholes collapsed instantly. A fraction of them might have been stabilized by this transient exotic matter, becoming the universe's first permanent time machines, forged in the fire of creation. If such structures did form and survive the universe's rapid expansion, their implications are staggering. They would provide a potential mechanism for the universe to self-seed. Information, or even matter, from a slightly later, more structured era could have traveled back to the earliest moments, influencing the initial conditions that gave rise to galaxies and stars. This could offer an explanation for why the universe seems so finely tuned for complexity. A primordial wormhole would be a relic of unimaginable power, a direct tunnel not just across the cosmos, but across time itself, potentially waiting to be discovered not as a structure in space, but as a unique gravitational signature or a mysterious anomaly in the flow of cosmic radiation. However, the existence of such a stable, traversable wormhole, a true time machine, runs into one of the most formidable theoretical obstacles ever proposed. This is the chronology protection conjecture, an idea famously put forward by Stephen Hawking. In essence, Hawking playfully suggested that the laws of physics must contain a built-in cosmic sensor whose job is to prevent time travel and thereby protect history from paradoxes. He argued that whenever a situation arises that could create a closed time-like curve, a path that loops back into its own past, something will always go wrong to stop it. The universe, it seems, has a profound allergy to paradox. The mechanism for this protection is as bizarre as time travel itself. It involves the strange behavior of the quantum vacuum. Empty space is not truly empty. It's a seething sea of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence, borrowing energy from the vacuum for an incredibly brief moment before annihilating each other and vanishing. This is a constant, frantic activity happening everywhere, all the time. Now, imagine this quantum foam near the throat of a wormhole that is on the verge of becoming a time machine. As a particle travels through the wormhole and back in time, it could potentially interact with its own past self. This creates a feedback loop where the same particle goes around and around the closed time-like curve, its energy building up with each pass. According to the mathematics, this feedback doesn't just increase a little, it diverges, shooting towards infinity. The vacuum fluctuations around the wormhole would be amplified to unimaginable levels, releasing an infinite amount of energy. This energy would not be a gentle glow, it would be a cataclysmic event. It would either cause the wormhole to collapse instantaneously into a singularity or create a gravitational shockwave so violent that it would tear the wormhole apart from the inside. In either case, the time machine would be destroyed the very moment it became possible to use it. Hawking's conjecture paints a picture of a universe with incredibly robust defensive systems, where the quantum laws themselves act as the ultimate paradox police, ensuring that cause always precedes effect. But does this protection have a loophole? Could the unique, unimaginable conditions of the universe's very first moments have temporarily suspended this cosmic rule? During the Planck era, the first 10 to the power of negative 43 seconds of existence, all the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces were unified into a single superforce. The energy densities were beyond colossal, and the very concepts of space and time as we know them break down. In this primordial furnace, the standard rules of quantum field theory, which underpin the chronology protection conjecture, might not have applied in their familiar form. The vacuum fluctuations themselves could have been in a different, more symmetric state, perhaps preventing the destructive feedback loop from ever starting. In this view, the early universe wasn't just a place where wormholes could form. It might have been the only place where they could become stable time machines without immediately triggering their own destruction. The Chronology Protection Agency might not have been open for business until the universe cooled and expanded enough for the forces to separate and for quantum field theory to settle into its modern rules. This opens up a tantalizing possibility that the first time travel event wasn't an accident, but a feature of cosmic infancy. A primordial wormhole could have allowed information or influence to flow from a slightly more mature region of the baby universe back to an even earlier instant, a process that could have played a crucial role in shaping the universe's initial conditions, fine-tuning them for the emergence of complexity. The very paradoxes we fear might have been essential tools in the construction of reality as we know it, used only once during a fleeting period when the usual safeguards were not yet online. Leaving behind the cosmic scale architecture of wormholes, we plunge into a realm where the rules of reality become profoundly strange, operating on a scale so small it defies our everyday intuition. This brings us to a phenomenon so bizarre that even Albert Einstein famously described it as spooky action at a distance. We are talking about quantum entanglement, a cornerstone of quantum mechanics that might hold clues to a very different kind of time travel, one not involving tunnels through space, but an instantaneous link that seems to laugh at our conventional understanding of time itself. To grasp entanglement, imagine a special machine that creates pairs of particles, say, two electrons. These particles are born together, intimately linked, and then they are sent flying off in opposite directions, perhaps across a room or across the entire solar system. Now, each particle has a property called spin, which you can loosely think of as a tiny arrow that can point up or down. According to quantum law, before we measure it, the particle doesn't have a definite spin. It exists in a blurry superposition of both possibilities at once. The magic happens when we measure one of the particles. The instant we pin down its spin, say, we find it pointing up. Its distant, entangled partner, no matter how far away it has traveled, instantly snaps out of its own blurry state and assumes the opposite spin, down. This connection is instantaneous, seeming to operate faster than the speed of light. The profound implication here is that the two particles behave as a single, unified system, regardless of the vastness separating them. This isn't like a radio signal, which takes time to travel. It's as if the space between them doesn't exist for this particular property, and this is where the tantalizing link to time emerges. If the correlation is truly instantaneous, then, from one perspective, the act of measurement on one particle could be seen as influencing the other's past. If the particles are light years apart, the measurement here might determine the state of the particle over there, and from the distant particle's point of view, that determining influence appears to have arrived from its future. It creates a situation where cause and effect, the bedrock of classical physics, become ambiguous. This has led some to speculate that entanglement might be a form of communication that transcends not just space, but time itself, a hidden network of connection woven into the fabric of the quantum world that operates outside our linear experience of past, present, and future. The natural next question is a thrilling one. Could we harness this spooky connection to actually send a message backwards in time? The idea would be to set up an experiment where an observer, let's call her Alice, decides on a message, a simple 1 or 0, and encodes it by choosing how to measure her entangled particle. Her partner, Bob, light years away, would then read the state of his particle, supposedly receiving the message instantly, and thus from his temporal reference frame, before any light speed signal from Alice could ever arrive. It seems like the ultimate communication system and a potential time machine. However, and this is the critical catch that most physicists emphasize, this is fundamentally impossible. The reason lies in the random, uncontrollable nature of the quantum measurement. When Alice measures her particle, she cannot choose whether it will be spin up or spin down. The outcome is completely random, like flipping a coin. She gets a random result, and Bob, upon measuring his particle, gets the correlated opposite result. But here's the problem. Bob just sees a random sequence of ups and downs. He has no way of knowing that his sequence is the opposite of Alice's, unless Alice sends him a separate, ordinary message, by radio, by laser, by carrier pigeon, telling him what her results were. Only by comparing the two lists, using a communication method that is limited by the speed of light, can they both see the perfect, spooky correlation. Bob cannot extract any meaningful information from his particle alone. He cannot tell if Alice has even made a measurement yet. The message is nothing but randomness until it is compared with a classical signal. Therefore, while the correlation is instantaneous, it cannot be used to transmit usable information faster than light, let alone backwards in time. This fundamental limitation is a powerful safeguard against the paradoxes that would otherwise run rampant. If we could send signals into the past, we could create situations where you prevent your own grandfather from meeting your grandmother, a logical inconsistency that physics seems adamant to avoid. The universe, through the subtle rules of quantum mechanics, appears to allow for spooky connections, but it carefully constructs them in a way that prevents any practical time travel messaging. The instantaneous link is real, but it is a correlation without communication, a connection that is useless for sending a deliberate signal. It's as if the universe has a private, instantaneous language that its fundamental particles use to stay in sync, but it's a language that we, as larger-scale observers, can only witness indirectly, never speak ourselves. Could this strange quantum synchronicity have played a role in the universe's first moments, the conditions immediately after the Big Bang, were a dense, hot soup of particles being created and annihilated in a frenzy? In such an environment, countless particle pairs would have become entangled. As the universe expanded and cooled at an incredible rate, these particles would have been stretched far apart across the nascent cosmos, carrying their spooky connection with them. This means the entire universe could be crisscrossed by a vast, ancient web of quantum entanglement, links forged in the first instance of time. Some theoretical physicists, like Juan Maldacena and Leonard Susskind, have even proposed that entanglement might be the fundamental source of the very geometry of spacetime itself. In this equals Epper conjecture, they suggest that a wormhole in Einstein-Rosen bridge is physically the same thing as a pair of entangled particles. This stunning idea implies that the spooky connection we see between particles is actually a microscopic manifestation of a tiny, non-traversable tunnel through spacetime. This perspective offers a radical new way to think about the first time travel. Perhaps the primordial universe wasn't filled with wormholes and time loops in the way we traditionally imagine. Instead, its entire fabric might have been a complex, deeply entangled network. The first time travel might not have been an event, but a condition of total quantum interconnection, where every point was instantly linked to every other point, blurring the distinctions of here and there, and by extension, now and then. In this view, the early universe wasn't a place where time travel occurred. It was a medium where time, as a linear sequence, hadn't yet fully crystallized from a more fundamental, timeless quantum reality. The spooky action we observe today in labs could be a faint echo of that primal, interconnected state, a remnant of a time when the universe was truly one unified whole, before expansion and cooling forced it to settle into the classical, well-behaved spacetime we experience today. But if quantum entanglement suggests a universe built on hidden connections, our next theory proposes that all of reality, including time, might be nothing more than a magnificent illusion. This is the holographic principle, an idea so radical it challenges the very nature of existence. To grasp it, we need to perform a mental experiment. Think about a credit card hologram, a flat, two-dimensional surface that, when light hits it just right, creates a stunningly realistic three-dimensional image. The holographic principle applies this same logic to the entire cosmos. It suggests that our rich, three-dimensional universe, with its galaxies, stars, planets, and even our own conscious experience, might actually be a projection. A cosmic mirage emanating from a distant, two-dimensional surface that contains all the information needed to describe everything within our volume of space. This isn't just a poetic metaphor, it's a serious proposal that emerges from the study of black holes. When matter falls into a black hole, it seemingly vanishes, and with it, the information that described that matter. This presents a paradox, as quantum mechanics insists that information can never be truly destroyed. The brilliant resolution, pioneered by physicists like Gerard T. Hooft and Leonard Susskind, was to realize that all the information about what falls into a black hole doesn't disappear. Instead, it gets perfectly encoded on the black hole's event horizon, the point of no return. The event horizon is a two-dimensional surface, yet it can store all the information about a three-dimensional volume of space. Our universe, according to the holographic principle, might operate on the same basic rule. we could be living inside a projection, with the true, fundamental reality existing on a vast, cold, two-dimensional boundary at the edge of the observable cosmos. This has a staggering implication for our understanding of time. In the holographic view, time, as we experience it flowing relentlessly forward, might not be a fundamental feature of the universe. Just like the third dimension of a hologram is an emergent property of the 2D surface, the arrow of time could be an emergent property of a more basic, timeless reality. On the fundamental 2D surface, the cosmic hard drive, there may be no past, present, or future. There is only information laid out in its entirety. The flow of time we feel could be a side effect of how this information is processed and decoded within the projected 3D world. It would be like watching a movie. The entire film exists on the reel all at once, but we experience it frame by frame, creating the illusion of a narrative unfolding. Our conscious awareness might simply be reading the cosmic data in a linear sequence. This perspective completely redefines the concept of time travel. If time is not a river to be sailed upon, but a dimension that emerges from a static block of information, then traveling through time is not about building a machine to propel you to the past or future. Instead, it becomes a matter of data access and manipulation. To time travel would be to gain the ability to read and rewrite the information on the cosmic hard drive. Changing the past wouldn't involve paradoxes of meeting your grandfather. It would be more like editing a line of code in a saved video game. You would simply be altering the data that defines what we perceive as a past event. The first instance of time travel, then, would be the very act of writing the initial data onto the cosmic surface. The moment the universe's information was first encoded, the Big Bang in this model, was the moment the timeline was set, and the illusion of temporal flow was set into motion. The Creator, or the initial conditions of existence, performed the ultimate act of historical programming. Could we ever find evidence for such an extraordinary idea? Surprisingly, scientists are actively looking. If our 3D world is a projection, there might be a fundamental limit to how much information any region of space can contain, a kind of maximum resolution for reality, much like a digital image becomes pixelated when you zoom in too far. This would manifest as a subtle, inherent fuzziness or graininess to spacetime at the tiniest possible scale, the Planck length. Experiments using incredibly precise lasers and gravitational wave detectors are searching for this very graininess, hunting for hints that space is not perfectly smooth, but composed of discrete, information-based units. Finding such evidence would be like discovering the pixels on the screen of our reality, a powerful clue that we are indeed living in a projected simulation, with time itself being part of the grand illusion. So if our reality is a projection, a cosmic film playing out in 3 dimensions, then the concept of the first time travel takes on a completely new meaning. It's no longer about moving through time, but about accessing and altering the source code. Think of the entire history of the universe, from the Big Bang to the present day and far into the future, as a completed movie reel. Every event, from the formation of the first star to your own birth, exists as a fixed sequence of frames on that reel. We, as conscious beings within the movie, experience it frame by frame, which creates our powerful, unshakable illusion of a flowing present moment. But from the perspective of the projector, the holographic boundary where the information is stored, the entire story is already written. In this view, to travel in time would be to somehow step outside the projection and rewind or fast forward the reel, or more radically, to physically edit the film itself. This leads us to a breathtaking possibility. The very first act of time travel wouldn't be a journey taken by a person or a particle within the universe. It would be the act of creating the initial conditions, the writing of the very first frame, the moment the cosmic projector clicked on and the first frame of our universe was illuminated. was the moment the entire timeline was set. But what if that first frame wasn't absolute? What if it could be edited? Changing that initial frame would be the ultimate form of time travel, because it would ripple forward, altering every single frame that comes after it. A tiny adjustment to the initial density, the strength of the fundamental forces, or the ratio of matter to antimatter in that first instant would create a completely different cosmic movie. Perhaps one where stars never formed, or where life was impossible, or where time itself flowed backwards. The first time traveler, then, would be whoever or whatever authored that first frame. This idea forces us to confront the deepest question in all of physics. Why do the laws of nature have the specific values they do? The constants of nature, the strength of gravity, the mass of an electron, the speed of light seem bizarrely fine-tuned. If any of them were even slightly different, the universe would be a lifeless void. In the standard view, this is just a brute fact, an unexplainable given. But in the holographic model, these laws aren't fundamental. They are part of the movie's script. They were chosen when the first frame was encoded. So, who or what was the screenwriter? One possibility is that our universe is one of a near infinite number of cosmic films, each with a different set of initial conditions, playing out in a vast multiverse. Most of these universes are dead and empty, but by sheer chance, a few, like ours, have the perfect settings for complexity and life to emerge. In this scenario, there was no conscious editor. Our universe's laws are simply the result of a cosmic lottery. Another, more provocative idea is that the act of observation itself plays a role in defining reality. This draws from the strange rules of quantum mechanics, where a particle's properties aren't fixed until they are measured. In the holographic context, this could mean that the universe's timeline wasn't fully rendered until conscious observers evolved within it to look at the film. Our own act of looking back in time through telescopes studying the early universe could be part of a feedback loop that solidifies the past. This doesn't mean we can change the past whimsically, but it suggests that the past and present are co-created in a more interdependent way than we ever imagined. The first time travel event, then, might be an ongoing process, with our own consciousness participating in the final rendering of cosmic history. Ultimately, the holographic principle transforms the search for the first time traveler into a search for the origin of physical law itself. It suggests that the answer won't be found by looking for a machine within the universe, but by deciphering the rules of the projector outside of it. The quest becomes one of understanding how information creates reality, and whether the initial data that spawned our cosmos was random, selected, or even somehow self-generated. Finding evidence for this perhaps by detecting the fundamental pixelation of spacetime wouldn't just rewrite the textbooks of physics, it would fundamentally alter our understanding of our own place in the cosmic story, revealing that our experience of time is a beautiful and profound illusion. Now, let's consider a cosmic phenomenon so strange it sounds like a thread pulled from mythology. We are entering the realm of cosmic strings, hypothetical relics from the universe's infancy that could have woven time loops directly into the fabric of reality. To understand these objects, we need to go back to a phase transition in the early cosmos, similar to when water freezes into ice. As the universe expanded and cooled, the fundamental forces we know today, gravity, electromagnetism, and the nuclear forces began to separate from a single, unified superforce. Physicists theorize that this process may not have been perfectly smooth. In some regions, the fields responsible for this symmetry breaking might have gotten stuck, unable to settle into the new, lower energy state that filled the rest of the cosmos. The result would be a cosmic string. Imagine a flaw in a vast crystal, a one-dimensional crack in spacetime of infinite density. These wouldn't be strings in the everyday sense. A single cosmic string thinner than a proton could have the mass of an entire mountain range compressed into every centimeter of its length. They would be under immense tension, and if they existed, they would have stretched across the newborn universe as it expanded, forming a vast, wriggling network. Their gravitational influence would be profound, and as they vibrated or snapped, they would have rippled spacetime itself, creating gravitational waves that might still echo through the cosmos today. But their most incredible property involves not just gravity, but the very structure of time. According to the mathematics of general relativity, the spacetime around a cosmic string is highly unusual. It's as if a wedge of space has been removed from around it, forcing everything to curve around a deficit angle. Now, consider the scenario proposed by physicist J. Richard Gott in the 1990s. He demonstrated that if two such cosmic strings were to pass by each other at a velocity approaching the speed of light, something extraordinary would happen in the region of spacetime between them. The combined gravitational fields of these two incredibly dense, moving objects would warp the fabric of reality so severely that they could twist time into a loop. This creates what is known as a closed time-like curve, or CDC. A closed time-like curve is exactly what it sounds like, a path through the universe that, if you were to follow it, would bring you back to the very same point in both space and time. It's a literal time loop built into the geometry of the cosmos. You wouldn't need a machine or a wormhole. The path itself would be a natural feature of the landscape, much like a river that flows in a circle. An object or a light beam traveling on this specific trajectory would find that its future inevitably leads to its past. This presents a scenario where the first time travel might not have been an accident of physics, but an act of discovery. The first intelligent civilization to arise in the universe, perhaps billions of years before life on Earth, might have been the ones to stumble upon this natural temporal pathway. The implications are staggering. A species advanced enough to detect the gravitational signature of cosmic strings and navigate the immense energies involved could have learned to use these natural time machines. They wouldn't have had to build one, they would have had to find one. This transforms the first time traveler from a passive particle caught in a quantum fluctuation into an active, conscious explorer. What would such a civilization do with this power? The possibilities are as vast as they are chilling. They might have sought to ensure their own survival by traveling back to a point before a cosmic catastrophe. They could have attempted to manipulate the initial conditions of their local universe to make it more hospitable, or perhaps their motive was pure knowledge, a desire to witness the birth of the cosmos firsthand. This idea also introduces a fascinating potential solution to the famous Fermi paradox, which asks, if the universe is so vast and old, where is everybody? One answer could be that they are not just out there in space, but they are also out there in time. An ancient, technologically sublime civilization may have transcended the normal flow of history altogether, using networks of cosmic string time loops to become effectively omnipresent throughout time, observing or interacting with the universe across eons without ever being easily detectable in our present moment. Their artifacts might not be buried on distant planets, but hidden in plain sight within the temporal folds of reality itself. Of course, the same formidable paradoxes we encountered before apply here with full force. The chronology protection conjecture suggests that the quantum effects around such a CDC would be catastrophic, generating infinite energy to destroy the loop. Yet once again, we must ask if the extreme conditions of the very early universe could have been a special case, if cosmic strings formed in the first fraction of a second after the Big Bang, the universe was still a seething, energetic plasma. The vacuum fluctuations that would later threaten to destroy a time loop might have been drowned out by the background fury of the cosmos, allowing these natural CTCs to exist, at least temporarily. This narrow window of opportunity, a brief period when the universe's natural defenses were down, could have been the only time such travel was truly possible, making the first time travelers not just ancient, but truly primordial. But what if the universe itself has a built-in safety mechanism, not to destroy time machines, but to make their paradoxes impossible from the start? This brings us to a theory that offers a radically different solution to the problem of changing the past, the Novikov self-consistency principle. Proposed by Russian physicist Igor Novikov in the 1980s, this principle is both elegantly simple and mind-bending in its implications. It asserts that if time travel is possible, then any actions taken by a time traveler were always a part of history. There are no alternate timelines, no branching realities, and no paradoxes, because anything a traveler does in the past must be consistent with the history that already led to their journey in the first place. The universe, in this view, is a single, immutable, and paradox-free story. Let's make this concrete with a classic thought experiment. Imagine you decide to build a time machine to travel back and prevent the assassination of a famous historical figure. You study the event meticulously, build your machine, and journey to the past. The Novikov principle dictates that you will inevitably fail, not because of guards or bad luck, but because the laws of physics themselves will conspire to ensure the outcome you know already happened. Perhaps your time machine malfunctions and arrives a minute too late. Maybe you slip on a banana peel at the crucial moment, or in a more dramatic twist, your very attempt to prevent the shooting is the accidental cause of it. Your presence distracts a guard, causing a chain of events that leads directly to the tragedy. Your actions in the past don't rewrite history, they fulfill it. You were always there, a hidden participant in the event you sought to change. Now, apply this logic to the grandest scale imaginable, the origin of the universe itself. The Novikov self-consistency principle suggests that if time travel occurred in the cosmos's first moments, it couldn't have created a paradox. It must have been an event that was always part of the cosmic script, seamlessly woven into the fabric of causation from the very beginning. This opens the door to a breathtaking possibility that the very existence of the universe relies on a time travel event that is perfectly self-consistent. This is the ultimate bootstrap paradox, a loop of causality with no true beginning, happening on a cosmic scale. Consider this scenario. What if the universe, in its early, hot state, contained the necessary conditions to generate a signal, a piece of information, or a quantum instruction that was then sent back in time, perhaps through a primordial wormhole or a quantum loop? This signal, arriving at the instant of the Big Bang, provided the exact parameters needed for the universe to develop in a stable, life-allowing way. The universe, in a sense, sent a message to itself to ensure its own successful creation. But here's the bootstrap paradox. Where did that information originally come from? It has no external source. It wasn't created by a god or a prior universe. It simply exists in a closed loop where the effect, the mature universe, is also the cause, the initial conditions. The information always was, and always will be, trapped in an eternal, self-justifying cycle. The Novikov principle makes this loop not just possible, but necessary. It guarantees that the message arrives correctly, because its arrival is what creates the universe capable of sending it. This idea offers a potential and deeply elegant explanation for one of the greatest mysteries in cosmology, the apparent fine-tuning of the universe. The fundamental constants of nature seem perfectly calibrated for complexity. If the force of gravity were even slightly stronger, the universe would have collapsed back on itself shortly after the Big Bang. If it were slightly weaker, galaxies and stars never would have formed. In the Standard Model, this is an incredible coincidence, but in a Novikov consistent universe, it's not a coincidence at all. It's the result of a cosmic feedback loop. The universe we observe is the only one that could possibly exist, because it is the only one that can consistently create the conditions for its own beginning. The first time travel wasn't an anomaly. It was the fundamental mechanism that locked in the laws of physics, ensuring a stable, coherent timeline from the outset. This perspective transforms our understanding of causality. We traditionally think of cause preceding effect in a straight line, but if the Nabokov principle is correct, causality can be a loop. The universe's first cause might also be its final effect. This doesn't require a conscious creator. It emerges naturally from the physics of a time travel-friendly cosmos. The principle acts as a cosmic editor, ensuring that the story of reality is free of plot holes. Any attempt to create a paradox would be like trying to write a sentence that contradicts itself. The universe simply won't allow the narrative to become inconsistent. In this grand, self-consistent timeline, the first time traveler wasn't a person or a particle, but the universe itself, performing the ultimate act of self-creation by ensuring its past and future are in perfect, unbreakable harmony. This idea of a self-creating cosmos takes the Nabokov principle to its most profound extreme, presenting us with what is known as the cosmic bootstrap paradox. The term bootstrap comes from the old phrase, pulling yourself up by your own bootstraps, an impossible feat that here becomes a description of reality's origin. It suggests the universe, in a very literal sense, created itself. To understand how this could work, let's dive deeper into the mystery of fine-tuning. The fundamental constants of nature, the strength of gravity, the mass of an electron, the precise value of the strong nuclear force are not arbitrary numbers. They appear to be exquisitely balanced on a knife's edge. If any one of them were altered by even a minuscule amount, the universe would be a sterile, lifeless void. For instance, if the force that binds atomic nuclei together were just a few percent stronger, all the hydrogen in the early universe would have fused into heavier elements almost instantly. Without hydrogen, there would be no water, no long-lived stars like our sun, and no chemistry complex enough for life. The odds of this perfect balance happening by random chance are astronomically low, leading many to wonder if there's a deeper reason. The cosmic bootstrap paradox offers a radical explanation that doesn't require an external designer. Imagine a future where a civilization, or perhaps the universe itself as a conscious, unified entity, reaches a state of ultimate knowledge and technological maturity. This intelligence, having comprehended all the laws of physics, realizes a startling truth. The universe can only exist if its initial conditions were set with incredible precision. So, this future intelligence devises a way to send a message, a packet of pure information containing the exact settings for the fundamental constants, back to the moment of the Big Bang. This message travels through a primordial wormhole or some other time loop mechanism, arriving at the very first instant to guide the unfolding of reality. The information acts as a seed, ensuring the universe evolves in a way that is stable, allows for galaxies and stars to form, and ultimately gives rise to the very intelligence that sent the message back. The loop is closed. The universe creates the conditions for the intelligence, and the intelligence creates the conditions for the universe. Where did the information originally come from? This is the heart of the paradox. It has no ultimate origin. It simply is, forever trapped in a closed, self-contained causal loop. There is no first cause. The universe is its own cause, a perfect, self-justifying system. The Nabokov self-consistency principle makes this not just a fanciful idea, but a logically coherent one. The principle guarantees that the message is sent and received perfectly because its successful transmission is an immutable part of history. Any attempt to alter the message would fail, as the failure would mean the intelligence that sent it never existed to make the attempt in the first place. The timeline is protected from paradox by its own rigid internal logic. This has staggering philosophical implications, most notably for the age-old debate about a creator. The bootstrap paradox presents a universe that is entirely self-sufficient. It eliminates the need for an external, uncaused cause, a prime mover, or a god to explain existence. The question, what created the universe, is replaced with the universe created itself through a temporal loop. This is not necessarily an argument for atheism, but rather for a different kind of cosmic autonomy. The universe becomes a necessary, self-referential truth, much like a mathematical equation that is true simply by its own internal consistency. The mystery of existence is not solved, but it is transformed from a question of who into a question of how, a how that involves the mind-bending physics of time loops. This perspective also redefines the concepts of purpose and design. If the universe is fine-tuned, the bootstrap paradox suggests the tuner was not an external entity, but the universe's own future potential. The purpose of the universe, in a sense, would be to eventually reach a state where it can comprehend itself so fully that it can secure its own existence. This imbues the cosmic story with a strange, recursive poetry. The long, arduous evolution of galaxies, stars, planets, and life is not a random accident, but a necessary journey the universe must undertake to become capable of its own creation. We, as conscious beings on that journey, are not merely bystanders. Our quest for knowledge, our drive to understand the cosmos through science, could be seen as an essential part of this cosmic feedback loop. By looking back in time with our telescopes and unraveling the laws of physics, we are participating in the very process that might have made our existence inevitable. In this view, the first time travel event is not a one-time occurrence in the distant past, but an ongoing, collaborative project between the universe and the consciousness it has spawned. While the idea of cosmic strings forming natural time loops is breathtaking, it relies on finding the right natural configuration. But what if a time machine wasn't a fluke of cosmic geography, but something that could, in theory, be engineered? This brings us to one of the most famous and purely mechanical concepts for time travel ever proposed, Tipler's cylinder. The brainchild of physicist Frank Tipler in the 1970s, this theory presents a blueprint for a time machine that operates on principles firmly rooted in Einstein's theory of general relativity, requiring no wormholes or mystical substances, just an almost unimaginable feat of engineering. The design is deceptively simple in concept. Imagine a cylinder, not just any cylinder, but one of truly cosmic proportions. It would need to be infinitely long, mind-bogglingly dense, and spinning at a significant fraction of the speed of light. Tipler calculated that for this to work, the cylinder would need to have a mass similar to that of our entire sun, but compressed into an incredibly long, thin, and incredibly strong rotating rod. The magic happens because of an effect predicted by general relativity known as frame dragging. Just as a spinning spoon in a cup of honey drags the liquid around with it, a massive rotating object drags the very fabric of space-time around it. For an object as dense and fast spinning as a Tipler cylinder, this frame dragging effect would be so immense that it would twist space-time into a helix, a corkscrew shape around the cylinder. Now, here is the crucial part. If you were to pilot a spaceship on a very precise, spiral path around this spinning cylinder, a path that follows the twisted spacetime, you could find yourself on a closed time-like curve. By completing a loop around the cylinder, you wouldn't just return to your starting point in space, you would return to your starting point in time. Each orbit could bring you further back into the past. The cylinder itself acts as a spindle around which time is wound into a loop. It's a starkly mechanical vision of time travel, one that turns the universe into a vast clockwork mechanism, where time is just another gear that can be reversed with the right leverage. Of course, the practical barriers are, to put it mildly, insurmountable with any technology we can envision. An infinitely long cylinder is obviously impossible to construct. Even a finitely long one would require materials with impossible strength to avoid collapsing under its own immense gravity into a black hole. Furthermore, keeping it stable and spinning at near light speeds is a problem of energy scales that dwarf the total output of every star in a galaxy. For these reasons, Tipler's cylinder is considered a theoretical curiosity, a proof of concept that time travel is not strictly forbidden by general relativity, even if it is practically unachievable for any civilization. But this is where we shift our perspective from engineering to cosmology. We are searching for the universe's first time travel event, a phenomenon that occurred under conditions far more extreme than anything we could ever create in a lab. So, let's speculate. Could nature have built its own Tipler cylinder in the violent infancy of the cosmos? The early universe was a forge for exotic objects of every kind. One compelling candidate is a primordial black hole. These are not the black holes formed from collapsing stars, but much smaller, far more ancient ones, thought to have been born from the intense density fluctuations in the first second after the Big Bang. Some primordial black holes could have had any mass, from a mountain to a planet, all compressed into a microscopic point. Now, consider a rapidly spinning primordial black hole. According to the laws of physics, all black holes are thought to possess spin, a remnant of the angular momentum of the material that formed them. A primordial black hole, born from the turbulent chaos of the early universe, could have been rotating at a significant fraction of the speed of light. While a black hole is a singularity, not a cylinder, the region just outside its event horizon experiences ferocious frame-dragging effects. In fact, there is a region around a spinning black hole called the ergosphere, where spacetime is dragged around so forcefully that it is impossible for any object to remain stationary. The physics here becomes incredibly complex, but it is conceivable that under the unique and still poorly understood conditions of the Planck era, a configuration of matter and energy, perhaps a dense, spinning knot of primordial fluid, or a field effect could have mimicked the necessary spacetime geometry of a Tipler cylinder, creating a transient closed time-like curve. This would have been a fleeting phenomenon. As the universe expanded and cooled in those first instants, the energy density would have dropped rapidly, and any such object would have either evaporated via Hawking radiation or been smoothed out by the inflationary expansion. But for a brief window, a narrow sliver of time just after the beginning, the universe might have been dotted with natural, self-assembled time machines. These wouldn't have been navigable by any conscious being. They would have been microscopic loops in spacetime, allowing particles or quantum information to briefly travel back in time. This could have created a web of causal connections, similar to the idea we explored with inflation, where the universe's initial conditions were set through a feedback process that involved these tiny, temporary time loops. The Tipler cylinder, therefore, transitions from a hypothetical machine for future engineers into a potential natural artifact of cosmic birth, a mechanism by which the infant universe could have communicated with its own recent past to ensure its own stable development. But what if the solution to every paradox isn't a cosmic editor enforcing a single timeline, but an infinite number of timelines where every possibility plays out? This brings us to one of the most daring and expansive ideas in all of physics, the many worlds interpretation of quantum mechanics, proposed by Hugh Everett in the 1950s. This theory offers a radical answer to the strange behavior of the quantum world. In the standard view, a particle exists in a blurry superposition of states until it is measured, at which point it randomly chooses one definite state. Everett's brilliant and to some unsettling suggestion was that the particle doesn't choose. Instead, at the moment of measurement, the entire universe splits. In one branch, the particle is measured as spin up, and in the other, completely separate branch, it is measured as spin down. Both outcomes are equally real, but they happen in parallel universes that, once split, can never interact again. Now, apply this logic not just to a single particle in a lab, but to every single quantum event that has ever happened. Every time an electron changes its energy level, every time a photon is reflected or absorbed, every random quantum fluctuation, each one is a fork in the road, spawning new universes. This means there is a universe where you decided to have toast for breakfast this morning, and another, just as real, where you chose cereal. There's a universe where the dinosaurs never went extinct, and another where life never arose on Earth at all. The cosmos becomes a constantly branching tree of infinite possibilities, a multiverse of staggering proportions where everything that can happen does happen somewhere. This completely redefines the very concept of time travel. In the many worlds view, you cannot travel back into your own past. That timeline is fixed and unchangeable. Instead, time travel would be a process of shifting between these parallel worlds. If you built a device to journey to what appears to be the year 1955, you wouldn't be arriving in the past of your own universe. You would be transitioning to a parallel universe that is nearly identical to yours, but whose timeline is lagging behind, currently experiencing the year 1955. In this new branch, you could interact with a version of your own grandparents, and any changes you make would not affect your original timeline. You might prevent their meeting in this new world, but that would simply create a new branch from that point forward, a universe where you were never born. Your home universe and your own history would remain completely untouched. This elegantly sidesteps the grandfather paradox altogether, because you're not altering history. You're merely tourism in someone else's. So, what would the universe's first time travel event look like in this model? It wouldn't be a journey, but a birth, the moment the very first significant branching of the cosmic timeline occurred. We need to look back to the universe's infancy, to an era of unimaginable energy and density, where quantum effects weren't just tiny curiosities, they were the dominant force shaping reality. The leading candidate for this primordial fork in the road is cosmic inflation. As we discussed earlier, inflation was a period of ultra-rapid expansion driven by a field called the inflaton. According to many models, this field didn't shut off uniformly across the entire cosmos. In some regions, it might have decayed from its high energy state, ending inflation and allowing for the hot Big Bang to begin. In other regions, it could have persisted, continuing to inflate. This is known as eternal inflation. The transition point between an inflating region and a non-inflating one would have been a quantum event of cosmic significance. It would have been the ultimate branching point, creating the first truly distinct universes within the greater multiverse. One branch became our observable universe, with its specific laws and constants. The other branches became entirely separate cosmic realms, potentially with different fundamental physics, different numbers of dimensions, and different destinies. This event, the first bubble nucleation in the eternal inflationary sea, was the multiverse's first act of time travel in the many worlds sense. It wasn't about moving through time, but about creating new streams of time, each with its own unique past, present, and future from the moment of its birth. The implications of this for our own existence are profound. The many worlds interpretation provides a powerful, if humbling, answer to the mystery of fine-tuning. We do not live in a universe that is miraculously fine-tuned for life. Instead, we simply inhabit one of the countless branches where the random roll of the quantum dice happened to produce the right conditions. In an infinite multiverse, it's statistically inevitable that some universes will have the perfect constants for stars, planets, and life to form. We find ourselves in one of those lucky ones not because of design, but by sheer necessity. Our universe's first and most significant time travel event was, therefore, the quantum fluctuation that led to the specific inflationary decay pattern that gave rise to our particular cosmic bubble with its life-friendly laws. Our entire reality is the result of that first, fateful branch. But how would such a jump between these infinite worlds actually work? It's one thing to say that universes branch, but it's another entirely to imagine a mechanism for moving between them. In the many worlds picture, this isn't about moving through a tunnel or a portal in the traditional sense. Instead, it's about a radical shift in your quantum state relative to the rest of reality. The key concept here is quantum decoherence. Think of it this way: when a quantum system is perfectly isolated, it can exist in a superposition of states, like Schrödinger's cat being both alive and dead. But the moment this system interacts with its environment, when a photon of light bounces off the box, or a molecule of air touches it, that fragile superposition collapses. More accurately, the system becomes entangled with the environment. The environment itself splits into two versions, one that has recorded the cat as alive, and another that has recorded it as dead. From the perspective of anyone within that environment, a definite outcome has occurred. This process of decoherence is what makes quantum probabilities solidify into the single, concrete reality we experience. Now, imagine scaling this up from a cat in a box to an entire person inside a time machine. For a conscious being to jump from one branch of the multiverse to another, a monumental event of decoherence would need to occur. The time machine itself, along with its occupant, would have to become entangled with a quantum system capable of creating a sufficiently large branching point. A sufficiently powerful and carefully controlled quantum event could, in theory, cause the entire local region of spacetime containing the machine to decohere into a new branch. From the traveler's perspective, they would simply activate their device and find themselves in a new reality, one that looks like the past, but is actually a newly created parallel world. They haven't rewritten history. They've emigrated to a different historical timeline. So, what kind of event could cause a branching on a scale significant enough to be considered the very first? We must look to the inflationary epoch, that brief period of hyper-expansion just after the Big Bang. During inflation, the universe was dominated by a quantum field, the inflatoned field. This field wasn't static. It was subject to tiny, random quantum fluctuations. These fluctuations were the original seeds from which all structure in our universe grew. A slightly denser patch of space here, due to a random fluctuation, would eventually gravitationally collapse to form a galaxy cluster. But these fluctuations were more than just density variations. They were fundamental choices. Each tiny, random jump in the value of the inflatoned field represented a decision point. A fluctuation in one region might cause the field to decay into the hot plasma of the Big Bang, while a different fluctuation in a neighboring region might keep it inflating. The very first significant branching of the multiverse, therefore, was likely one of these primordial quantum fluctuations. It was the moment a random jitter in the inflatoned field, in a specific patch of the newborn cosmos, tipped the scales and dictated the fundamental properties of our local reality. Did that fluctuation result in 3 dimensions of space, or 4? Did it set the strength of the electromagnetic force to one value or another? That single, random quantum jump didn't just create a galaxy. It created an entire timeline with a specific set of physical laws. All the other possible outcomes, the universes with stronger gravity, with 5 fundamental forces, with time that flows backwards, were spun off into their own separate, equally real branches at that exact instant. The first time travel event in the many worlds sense wasn't a journey taken by anyone. It was the universe's first major decision, a roll of the quantum dice that carved out our particular cosmic story from an infinite tapestry of possibilities. Our existence in this specific universe, with its specific laws, is the direct result of that first, fateful branch. But to truly challenge our sense of a flowing present, we must confront a theory that is both mathematically elegant and philosophically jarring: the block universe. This concept, also known as the four-dimensional universe or eternalism, emerges directly from Einstein's theory of relativity. It proposes that the distinction we feel between past, present, and future is a profound illusion, a trick of our conscious perception. In reality, the entire timeline of the cosmos, from the Big Bang to the very end of everything, exists all at once, as a single, static, four-dimensional structure. Think of it not as a movie reel that is being played, but as a complete DVD. Every scene, from the opening credits to the final frame, is already there, fixed and unchanging. Our conscious experience of moving through time is merely the laser of our awareness reading the disc sequentially, creating the convincing sensation of a flowing now. In this model, the universe is a block because it combines the three familiar dimensions of space with the dimension of time into a single, seamless whole. An event is not something that happens at a point in time. It is a fixed coordinate within this four-dimensional continuum, with a specific location in both space and time. Your birth, your first day of school, and every moment of your life up to this second, as well as every future event that will ever occur, all exist with the same concrete reality. They are simply located at different temporal addresses within the block. This is not just a philosophical idea. It's a direct consequence of relativity, which shows that the concept of a universal now is relative to an observer's motion. Two events that are simultaneous for one person may not be for another moving at a different speed. The block universe is the only framework that can coherently accommodate this relativity of simultaneity. So, what does time travel mean in such a universe? It becomes a complete misnomer. If everything already exists, then you cannot travel to a time that isn't already there, waiting for you. Instead, time travel would simply be the ability for a conscious entity to move its point of view through the four-dimensional block in a non-sequential way. It would be like scanning a barcode. The laser light moves along the code, reading the information in a set order. But what if the laser could jump back to a previous line or skip ahead to a future one? The information on the barcode itself doesn't change, only the path of the reader does. In the block universe, a time traveler wouldn't be changing history any more than you change a book by turning to a different page. They would simply be reorienting their consciousness to a different, pre-existing part of the cosmic structure. This leads to a startling conclusion about the first time travel event. In a universe where all of time is equally real, the idea of a first anything becomes problematic. The event of a conscious being first navigating the time dimension would itself be a fixed point within the block. From an external, God's eye view, that event has always been there. Therefore, the first time travel isn't an event that happened in the past. It is an eternal feature of the universe's geometry. It's like asking for the first point on a circle. The question doesn't make sense because the circle has no beginning. The moment an entity gains the ability to consciously experience events out of order is simply a coordinate within the block, as real and unchanging as the Big Bang itself. The journey is not through a river of time, but across a frozen landscape of events. This perspective offers a powerful, albeit disquieting, solution to the paradoxes that plague other time travel theories. The grandfather paradox simply cannot occur. If you travel to the past to prevent your grandfather from meeting your grandmother, your actions were always a part of the timeline. Your attempt fails, or perhaps your interference was the very cause of their meeting. The timeline is a single, unchangeable story, and your time-traveling adventure is just a chapter that was always written. The Nabokov self-consistency principle. which we discussed earlier, finds its perfect home in the block universe. The universe isn't actively preventing paradoxes. It's just that paradoxes are logically impossible in a reality where all events are fixed. Cause and effect are still valid, but they are laid out eternally, like a cosmic domino chain, where every domino has already fallen in a predetermined sequence. The profound implication of the block universe is that free will, as we commonly understand it, might be an illusion. If the future already exists in a concrete way, then our choices are not truly free. They are just us discovering the path that was always laid out for us. This is a difficult pill to swallow, but some philosophers and physicists argue that our feeling of making choices is real, even if the outcome is fixed. The experience of deliberation and decision-making is itself a part of the unchanging block. We are like characters in a novel who believe they are making their own decisions, unaware that their entire story has already been written. The author, in this case, is the initial conditions of the universe and the immutable laws of physics. So, how could a conscious entity actually navigate this static block? The mechanism wouldn't be a machine that propels you through time, but a technology or a natural ability that alters your world line. Your world line is your unique path through the four-dimensional block, the continuous thread that connects your birth to your death. Normally, this line moves relentlessly forward through the time dimension. To time travel, you would need a way to bend your world line, making it loop back on itself or jump ahead. This might involve manipulating gravity on a colossal scale, using something like a Tipler cylinder or a rotating black hole to create a closed time-like curve that your consciousness could follow. Alternatively, it might involve a method of shifting your conscious awareness from one point on your world line to another, effectively teleporting your point of view through time while your physical body remains on its fixed path. The first instance of this happening would be the moment a being's world line first developed a kink or a loop. But remember, from the perspective of the block, that kink was always there. The being who accomplishes this feat doesn't create a new reality. They simply become aware of the full, timeless nature of the reality they have always inhabited. They awaken to the fact that they are not a raft on a river, but a sculpture in a museum of time, and they have just learned how to walk between the exhibits. This transforms the quest for the first time traveler from a search for a historical event into a search for the first moment of cosmic enlightenment, the instant a mind grasped the true architecture of existence and learned to navigate it freely. This idea of a predetermined universe, where every moment from the Big Bang to the heat death of everything is equally real, forces us to confront one of the most deeply felt aspects of our existence, the sensation of free will. It feels, with every fiber of our being, that we are making genuine choices, that you could have chosen to watch this video at a different time, or that you could put it on pause right now. This feeling of agency is powerful and persuasive, but if the block universe is correct, then the choice you made to click on this video was already encoded in the four-dimensional fabric of reality billions of years ago. Your entire life's path, with all its triumphs and tribulations, is a fixed thread woven into the cosmic tapestry. This presents a profound philosophical dilemma. Are we truly the authors of our own stories, or are we merely reading from a script that was written at the dawn of time? To navigate this, we need to distinguish between two levels of reality. On the fundamental, physical level, the block may indeed be static. The laws of physics, acting on the initial conditions of the universe, determine every subsequent event in a chain of cause and effect that is unchangeable. However, on the level of our conscious experience, free will might still have a very real meaning. Our brains are incredibly complex biological computers that take in sensory data, process it through the lens of our memories and desires, and produce a decision. The process of deliberation feels like free will because it is a real, physical computation happening in real time, even if the outcome of that computation is predetermined from a cosmic perspective. The experience of going through the process is not an illusion. It is the actual, physical manifestation of causality at work within your mind. In this view, you are free to make the choices you were always going to make. Your will is not free from the laws of physics, but it is free from external coercion. You are the system that is doing the deciding. So, where does this powerful, universal illusion of a flowing present come from? Why do we experience time as a relentless river carrying us from a fixed past into an open future, rather than as the static landscape the block universe suggests? The answer likely lies not in the laws of physics, but in the quirks of our own biology and psychology. Our conscious awareness seems to be a process that works by creating a working model of reality. The brain doesn't present the world to us in real time. There's a slight delay as our senses gather information and our neurons fire. To create a coherent experience, the brain constructs a narrative, stitching together sensory inputs from the very recent past into a seamless sense of now. This present moment we feel is actually a calculated reconstruction of what happened a fraction of a second ago. It's a trick of perception, a user interface that our consciousness uses to navigate the world effectively. This model is brilliantly adaptive. By having a clear sense of past and future, we can learn from experience and plan for what's to come. The feeling that the future is open is essential for motivation. If we believed everything was predetermined, why would we ever strive, create, or care about consequences? The illusion of the flowing present is therefore not a flaw in our design, but a crucial feature for a species that survives by anticipating outcomes. It's the psychological engine of causality. We remember a past cause, we experience a present effect, and we project a future consequence. This linear narrative is the very structure of our thought. But it might be just that a story our brains tell us, a necessary simplification of a far more complex, timeless reality. This leads us to a truly revolutionary definition of what the universe's first time travel event could be. If our ordinary experience of time is a biological construct, a kind of virtual reality interface generated by our brains, then transcending that interface would be the ultimate form of time travel. The first time travel might not involve machines or wormholes at all. It could be the moment a consciousness, whether biological or artificial, achieves a state of awareness so advanced that it can perceive the universe in its true, four-dimensional state. Imagine a mind that could step outside its own sequential processing. Instead of experiencing life frame by frame, it could see the entire film at once. Your birth, your life, and your death would be simultaneously present, like landmarks on a map that you could survey from a great height. What would this be like? It's almost impossible for our linearly wired brains to comprehend. It wouldn't be like watching a fast-forwarded video of history. It would be a mode of perception where the concepts of before and after lose their meaning. Such a consciousness wouldn't travel to the past. It would simply direct its attention to it, as easily as we turn our head to look at something in another part of a room. The past and future would be locations, not events. For this entity, the death of the last star would be as immediately accessible as the memory of its own creation. This would be the ultimate enlightenment, a liberation from the tyranny of the clock. The first being or civilization to achieve this would not be building a time machine. They would be undergoing a profound cognitive evolution, learning to see the universe as it truly is, rather than through the narrow, survival-oriented filter of conscious experience. This concept of perceiving the block universe ties directly into some of the most speculative ideas in theoretical physics and philosophy. The physicist Julian Barber, for instance, has proposed that time is fundamentally an illusion. and that the universe is simply a vast collection of every possible now, which he calls time capsules. From this perspective, the flow of time is just our conscious journey from one of these static configurations to another. The first time traveler would be the first entity to become aware of this entire collection simultaneously. Furthermore, this idea resonates with certain interpretations of quantum mechanics that suggest conscious observation plays a role in collapsing quantum possibilities into definite realities. If that's the case, then a consciousness that could see the entire block might not just be a passive observer, but an active participant in a much deeper cosmic process, one where the past, present, and future are co-created in a single, timeless act of perception. The journey to understand time travel, therefore, may ultimately be a journey inward toward unlocking the deepest potentials of consciousness itself. But if navigating the timeless block of the universe represents one extreme, our next theory takes us in a completely opposite direction, proposing that time's arrow isn't an illusion, but a fundamental force that can be literally reversed. We've spent a lot of time discussing black holes, those cosmic vacuum cleaners from which nothing, not even light, can escape. But what if there is an equal and opposite phenomenon? Imagine a black hole running in reverse, a region of spacetime from which nothing can enter, only explode outward. This is the tantalizing concept of a white hole. Where a black hole's event horizon is a point of no return, a white hole's horizon would be a point of no admission. It would violently expel all matter and energy that approaches it, acting as a cosmic fountain of infinite energy, a natural Big Bang on a smaller scale. The mathematics of general relativity, the very same equations that predict black holes, are perfectly symmetric and allow for such white hole solutions. They are just as valid, mathematically speaking, yet we have never observed one. The reason is tied to the second law of thermodynamics, which states that entropy, or disorder, always increases. A black hole, with its immense gravity sucking order into a tiny point, is a perfect entropy-increasing machine. A white hole, which would seem to spew out ordered energy, would appear to decrease entropy, making it extraordinarily unlikely to form naturally after the universe began. But this very improbability leads to a fascinating possibility. White holes couldn't form in our universe's future, but they might be intimately connected to its past. This idea leads to one of the most elegant connections in all of cosmology. If you take the mathematical description of a black hole and simply reverse the direction of time in the equations, you get a white hole. This has inspired the profound suggestion that a black hole in one region of spacetime could be connected to a white hole in another. Think of it as a cosmic relay race. A black hole is the finish line where matter and energy are collected. That information doesn't just vanish. According to this theory, it is passed through a tunnel, a wormhole, and handed off to a white hole, the starting line in a different part of the cosmos, or even in a completely different universe. The black hole's crushing singularity in our future becomes the white hole's explosive birth event somewhere else. Now, let's scale this idea up to the absolute maximum. What is the single most energetic, explosive, and foundational event we can point to in the history of everything? The Big Bang. It was a moment when all the matter and energy in the observable universe erupted from an incredibly hot, dense state. This bears a stunning resemblance to the theoretical description of a white hole. So, could the Big Bang itself be the ultimate white hole? In this breathtaking scenario, our entire universe isn't the result of a spontaneous creation from nothing, but the output nozzle of a white hole. The singularity from which we emerged would be the endpoint of a gravitational collapse in a parent universe. Our cosmic genesis would be the other side of a cosmic death in a separate reality. This transforms the Big Bang from a true beginning into a transitional phase. Our universe would be one bubble in an infinite chain. connected to a larger multiverse through a network of black hole and white hole tunnels. But the temporal implications are even more radical. If our Big Bang was a white hole, then what we perceive as the beginning of time for us could be the end of time for another cosmos. The arrow of time in our universe, pointing forward from the Big Bang, would be inherited. It would be a continuation of the thermodynamic arrow from the parent universe that spawned us. In a sense, our future is the afterlife of another universe's past. This leads to the most mind-bending proposition of all, that a black hole in one universe could be connected to a white hole not in a separate universe, but in its own past. This would create a breathtakingly beautiful, yet profoundly paradoxical, loop of causality. Imagine a massive star in the early universe collapsing into a black hole. Instead of forming a singularity that crushes everything into oblivion, it connects via a wormhole to a white hole that erupts at an earlier point in time. That eruption provides the very material and energy that, after billions of years of stellar evolution, forms the star that collapses to create the black hole in the first place. The entire cosmic story, from the star's birth to its death and rebirth, would form a closed loop in time. It would be a universe that literally creates itself, a perfect Ouroboros, the snake eating its own tail, but on a cosmological scale. While this idea of a self-creating universe is mathematically intriguing, it confronts the same paradox problems we've seen before. How can an effect, the white hole's explosion, precede its cause, the black hole's collapse? The Novikov self-consistency principle could, once again, provide a framework, forcing the loop to be perfectly consistent. But the energy requirements and stability issues are, needless to say, far beyond anything we can test. However, the white hole model offers a compelling, if speculative, answer to the question of what preceded the Big Bang. Instead of an empty void or a quantum fluctuation, there was a universe, perhaps very different from our own, living out its life until one of its black holes initiated a new cosmic cycle, with our universe as its offspring. The search for the first time traveler then becomes a search for our cosmic parent, and the answer might be that we are all, in a way, time travelers, born from the end of another world's time. So if our universe is the white hole eruption of a black hole collapse in a parent cosmos, we are forced to ask an almost unthinkable question. What was that other universe like? What laws of physics governed it? And crucially, how did time behave there? One of the most radical possibilities is that the arrow of time in that parent universe was reversed relative to our own. In our cosmos, time's direction is inextricably linked to the increase of entropy, the progression from order to disorder. We see an egg smash, but we never see the pieces reassemble themselves. But if our Big Bang was the output of a white hole, it represents a massive, instantaneous injection of order, a state of incredibly low entropy. For this to be consistent, the universe that spawned us must have been evolving towards a state of higher order, its entropy decreasing as it approached its final state, the colossal black hole collapse that became our beginning. From the perspective of that parent cosmos, time would have felt like it was flowing backwards from our point of view. A being living there would watch shattered eggs spontaneously reassemble and remember events of tomorrow while anticipating the past. It's a concept that stretches the mind to its breaking point, suggesting that our unidirectional experience of time might be a local, not a universal, phenomenon. This idea of a universe with a reversed thermodynamic arrow immediately crashes into one of the most fundamental laws of physics, the second law of thermodynamics. This law isn't a suggestion, it's a statistical imperative that disorder must increase over time. A universe where entropy consistently decreases is like a river flowing uphill. It seems to defy the very nature of reality as we understand it. How could such a cosmos even function? The resolution to this paradox might lie not in breaking the second law, but in redefining the scale at which it applies. Imagine the entire multiverse as a closed system. Within this grander structure, the total entropy always increases, but individual universes within it could act like temporary eddies in a flowing river. While the river as a whole moves downhill, a small whirlpool can temporarily exhibit local motion that seems to go against the current. A parent universe with decreasing entropy would be one of these eddies, a temporary fluctuation away from equilibrium. Its journey towards order would be balanced by our universe's explosive journey towards disorder, ensuring that across the entire multiverse, the second law remains inviolate. To make this more than a philosophical escape, we need a theory that can describe the physics of the singularity, the moment of transition between the black hole and the white hole. This is where our current theories, general relativity and quantum mechanics, break down completely. We need a theory of quantum gravity, and one of the leading candidates, loop quantum gravity, offers a fascinating and concrete model for this very process. In LQG, spacetime is not smooth and continuous, but is composed of tiny, discrete loops, a fabric woven from individual threads. This granular nature of space and time prevents the formation of a true, infinitely dense singularity. Instead, as matter collapses into what would become a black hole, the repulsive force of quantum gravity becomes unimaginably strong at the Planck scale, acting like a cosmic trampoline. The collapse doesn't end in a point of infinite density. It rebounds. The black hole's singularity is transformed into a white hole's Big Bang. In this framework, often called the Big Bounce, our universe isn't the first, but simply the latest in an endless cycle of expansion and contraction. Each cycle inherits a small amount of quantum information from the previous one, meaning the parent universe wasn't some alien realm with reversed time, but a cosmos very much like our own, just older, whose death became our birth. The implications of this are staggering for the concept of the first time travel. If the universe cycles through bounces, then the very first cycle, the original universe, could have been influenced by its own future. Information from a subsequent cycle could, in principle, be imprinted on the quantum state of the universe during the bounce, traveling backwards across the temporal boundary to fine-tune the initial conditions of the next cycle. This would mean the first true time travel event wasn't something that happened within a universe, but was an integral part of the cosmic reproductive process itself. The universe fine-tunes its own initial conditions for the next iteration, creating a form of cosmic evolution where each subsequent universe is better adjusted for longevity and complexity. In this view, the fine-tuning we observe isn't a miracle, but the result of countless cycles of trial and error, with time-traveling quantum information acting as the mechanism for inheritance. We may live in a universe that is the product of its own future, a thought that inverts our entire understanding of causality and suggests that the ultimate purpose of the cosmos might be to learn how to create itself. But if the cosmos can loop and rebound, and if time itself might be an emergent property, then we must confront a truly humbling possibility that our very presence as observers might be the most important factor in the story. This brings us to a principle that is as profound as it is simple, and one that could hold the key to why time travel, if it exists, hasn't rewritten the history books. It's called the anthropic principle. In its most basic form, it states a simple, almost tautological truth. The universe we observe must be compatible with our existence as observers, because if it weren't, we wouldn't be here to observe it. We find ourselves in a universe with the right constants for life, not necessarily because it was designed for us, but because we are a product of its specific, life-allowing conditions. It's like a fish marveling at how perfectly water is suited for its gills. The water wasn't made for the fish. The fish evolved to live in the water. Now, apply this razor-sharp logic to the problem of time travel. Imagine a universe where time travel is technically possible, but where the act of changing the past is inherently unstable. In this cosmos, countless would-be time travelers might have attempted to journey into history. Most of these attempts, however, would have resulted in paradoxes. A traveler goes back and prevents their own birth, creating a logical inconsistency that the universe cannot sustain. According to the anthropic principle, we would never know about these failed attempts. Why? Because those paradoxical timelines are ones in which we, the observers, could never come to exist. They are branches of reality that either collapse instantly or are shunted off into dead ends, universes devoid of the conscious life needed to report on the failure. The only time travel events that can leave a lasting mark on a stable cosmos are those that are perfectly self-consistent. This leads to a fascinating and powerful selection effect. The first successful time travel event, the one that actually becomes part of the historical record we study, would, by definition, have to be an event that does not create a paradox. It must be an action that seamlessly integrates into the timeline, causing no disruption to the chain of causality that led to the time traveler's own existence. Think of it as a cosmic filter. Out of a near infinite number of potential time-traveling actions, the vast majority are weeded out because they lead to logical inconsistencies. The tiny fraction that remain are the ones that are paradox-free. So, when we look back at history and see no obvious evidence of meddling from the future, it doesn't prove that time travel is impossible. It might simply mean that we are living in the one version of history that was robust enough to withstand it, the timeline that was never successfully altered in a way that erased us. This idea offers a potential solution to the most frustrating aspect of time travel, the Fermi paradox for historians. If time travel is possible, where are all the time tourists? Why aren't our history books filled with anachronisms and visitors from the future? The anthropic answer is that they very well might be here, but their presence is necessarily subtle and self-concealing. A time traveler's actions must be so carefully woven into the fabric of events that they are indistinguishable from ordinary history. Perhaps a crucial piece of advice given to a leader, a timely invention inspired by a dream, or a narrowly avoided disaster, was actually the work of a visitor from the future, ensuring that their own timeline remained intact. The most successful time travel would be invisible, leaving no clear fingerprint that could create a paradox. The first time travelers wouldn't be flamboyant figures changing the course of empires. They would be ghostly editors, making tiny, crucial corrections to the cosmic manuscript to ensure the story still gets written. This perspective also reframes our search for evidence. We shouldn't be looking for glaring contradictions in the historical record. Instead, we should search for moments of incredible, almost miraculous, good fortune that seem to defy probability. Events where the right person was in the right place at the right time against all odds, or where a scientific discovery was made in a sudden, inexplicable leap. These could be the subtle signatures of a self-consistent time travel event, a nudge from the future that ensured a particular path was taken. The anthropic principle suggests that our entire reality might be the product of a kind of temporal natural selection, where only the most logically coherent timelines survive to produce observers who can ponder their own origin. In this view, the first time travel wasn't a singular event that happened once, but an ongoing process of cosmic editing, where the future gently guides the past to ensure its own stable existence. This idea of the universe as a carefully edited timeline, filtered by the anthropic principle to avoid paradox, leads us to an even more ambitious thought. We've considered that the laws of physics seem bizarrely fine-tuned for the existence of life. But what if that's only a secondary effect? What if the primary reason the cosmos has its specific set of rules is not for us, but for something that comes after us. What if the universe is fundamentally structured to allow for the eventual development of time travel itself? In this view, life, and particularly intelligent, technologically curious life, is not the ultimate goal, but a crucial intermediate step, a necessary catalyst for the universe to achieve its true potential, becoming aware of its own entire history and gaining the ability to navigate it. Think about the prerequisites for building a time machine. Even in theory, it requires a universe with stable laws of physics that can be understood and manipulated. It needs a cosmos that lasts long enough for intelligence to evolve and technology to advance to a godlike level. It demands fundamental forces that allow for the extreme warping of spacetime without immediately collapsing into chaos. The weak nuclear force, for instance, must be precisely calibrated to allow for the long-lived stars that create the heavy elements essential for planets and life. If it were even slightly stronger or weaker, stars would burn out too quickly or never form at all, leaving no one around to even dream of time travel. The cosmological constant, which drives the acceleration of the universe's expansion, must be incredibly small. If it were large and positive, the universe would have ripped itself apart before galaxies could form. If it were negative, it would have collapsed back in on itself eons ago. This precise balance creates the vast, long-lived cosmic stage necessary for a slow, gradual ascent towards technological maturity, but it goes deeper than just providing a stable environment. The very laws that enable time travel might be baked into the universe's foundation. General relativity, which allows for the possibility of wormholes and closed time-like curves, is a feature of this particular cosmos. Its equations are a specific recipe that, when combined with quantum mechanics, might permit temporal loops in a universe with a different set of physical laws. The very concept of bending time might be as nonsensical as dividing by zero. Our universe, then, could be one of the very few in the multiverse where the mathematical potential for time travel is even encoded in the fundamental software. The constants aren't just tuned for life, they are tuned for a specific kind of physics that allows for spacetime to be manipulated in this ultimate way. We are here because the universe is time travel friendly, not the other way around. This transforms our role from accidental inhabitants to essential participants in a cosmic destiny. Our purpose in this grand scheme would be to act as the universe's nervous system, the mechanism by which it develops self-awareness across time. We are the universe's way of learning about itself, and the pinnacle of that learning would be achieving a perspective outside of the linear flow of time. The long march of evolution, the rise of civilization, the scientific revolution, all of it could be seen as a necessary step-by-step process to build the knowledge and tools required to finally crack the code of temporal navigation. The first cell, the first fish to crawl onto land, the first human to gaze at the stars, each was a milestone on the road to building the first time machine. This leads to a fascinating potential resolution for the Fermi paradox. If the universe is fine-tuned for time travel, then the reason we don't see advanced civilizations out among the stars might be because they don't occupy space in the way we expect. A civilization that has mastered time travel would have transcended ordinary interstellar travel. Why bother crossing the immense distances between stars when you can simply move to a time when your planet was closer to another star, or when the galaxy was more densely packed? Their artifacts wouldn't be ancient ruins on distant planets. They would be temporal artifacts hidden in the folds of history. They might be observing us not from another world, but from another century, their presence perfectly integrated into the timeline to avoid paradox. The great silence of space might be because everyone who matters has already graduated to manipulating time. Ultimately, this idea offers a new answer to the ancient question of why we are here. It suggests that the universe has a hidden function, a latent capability waiting to be activated. We are not just random assemblages of atoms in a purposeless cosmos. We are part of a cosmic project of such grandeur that it is almost impossible to comprehend, the project of liberating consciousness from the prison of the present moment. The fine-tuning we observe is the universe setting the stage for its own greatest act. The first time travel event, therefore, would not be an isolated technological breakthrough. It would be the universe, through us, finally waking up to its own true nature as a four-dimensional block and taking the first tentative steps toward exploring the vast, timeless landscape that it has always been. But to truly bend time, you need more than just immense gravity. You need gravity in motion. This brings us to a specific and theoretically fascinating type of black hole that could serve as the ultimate natural time machine, the Kerr black hole. Named after the mathematician Roy Kerr, who discovered the solution to Einstein's equations in 1963. This isn't your average, garden-variety black hole formed from a collapsing star. A Kerr black hole is one that possesses angular momentum. It's spinning, and that rotation changes everything about its internal structure, while a non-rotating black hole crushes everything that crosses its event horizon into a single point of infinite density, a terrifying singularity. A rotating Kerr black hole is a far more complex and potentially navigable object. Its singularity is not a point, but shaped like a ring, a dizzying loop of infinitely warped spacetime. Think of the difference between falling into a still pond versus being caught in a powerful whirlpool. The still pond simply pulls you under, but the whirlpool has a complex, dynamic structure. In the case of a Kerr black hole, the spinning motion drags spacetime around with it so violently that it creates a region just outside the event horizon called the ergosphere. Here, nothing can remain stationary. Space itself is flowing like a raging river. More importantly, the ring singularity at the center isn't surrounded by the same crushing gravitational forces as a point singularity. The mathematics of general relativity suggest that an object on a precisely calculated trajectory could, in theory, pass through the ring itself without being annihilated. It's like threading the eye of a cosmic needle, where the needle is a loop of impossible physics. So, where would such a journey lead? The equations point to two breathtaking possibilities. The first is a journey into a universe of negative space. This isn't just empty void. It's a realm where the normal rules of geometry are inverted, and distances could be negative. The second, and for our purposes more compelling, possibility is that the ring singularity acts as a gateway to a different time. The intense frame dragging and the unique geometry of the rotating black hole could create a stable, closed, time-like curve within its interior. An object passing through the ring might not emerge elsewhere in space, but elsewhere in time, perhaps deep in the past or far into the future. The Kerr black hole, then, isn't just a cosmic trapdoor. It's a potential revolving door through the ages, a natural feature of the universe that could, under the right conditions, serve as a time portal. This leads to a profound speculation. What if the universe's first instance of time travel wasn't a random quantum event or a feature of the Big Bang, but a deliberate act of exploration by a supremely advanced civilization? Imagine a species that reached a technological pinnacle not just millions, but billions of years before our sun even ignited, having mastered interstellar travel and harnessed the energy of galaxies. Their final frontier wouldn't be space, but time itself. They would have scanned the cosmos for natural phenomena that could facilitate such a journey, and the Kerr black hole would be the most promising candidate. The challenge would be monumental. Navigating to the ring singularity would require unimaginable precision and shielding to withstand the ferocious tidal forces and radiation. It would be the ultimate cosmic daredevil stunt. The successful transit through a Kerr black hole's ring singularity would therefore represent the first time travel event in a very specific sense, the first successful, navigated, and purposeful journey through time. This wouldn't be a microscopic particle briefly looping back on itself. This would be a conscious act by intelligent beings to step outside the linear flow of history. The moment their vessel passed through the ring would be a landmark moment in cosmic history, the instant the universe's potential for time travel was first realized by a mind capable of understanding it. They wouldn't be altering the past in a clumsy way. Their initial foray would likely be one of pure observation, a cautious step into the timeline to witness events without interfering, adhering to a self-consistent model to avoid paradox. The very fact that we exist in a coherent timeline could be indirect evidence that such pioneers, if they ever existed, were incredibly careful and wise in their use of this ultimate power. To truly comprehend how a Kerr black hole could function as a gateway, we must venture beyond the event horizon and into one of the most dynamic regions in all of existence, the ergosphere. Imagine the event horizon as the ultimate point of no return, a spherical boundary from which even light cannot escape. But surrounding this dark sphere is a football-shaped region of distorted space, the ergosphere, where the black hole's furious rotation creates a phenomenon that defies intuition. Here, spacetime itself is not just curved, it is being dragged, pulled along with the spin of the black hole in a maelstrom of such force that nothing, absolutely nothing, can remain stationary. It's as if you were trying to stand still on a merry-go-round, spinning at nearly the speed of light. The very fabric of reality is moving beneath your feet, forcing you to rotate with the cosmic current. This is the power of frame dragging pushed to its absolute extreme, a testament to how mass and motion can twist the universe into knots. Within this chaotic whirlpool of twisted spacetime lies a potential power source of almost unimaginable scale, the Penrose process. Conceived by the renowned physicist Roger Penrose in 1969, this is a theoretical method for extracting energy directly from a rotating black hole. The process relies on the unique properties of the ergosphere, since particles within this region are forced to move with the rotating spacetime. They possess what is known as negative energy relative to a distant observer. Here's how it could work. Imagine an advanced civilization sends a probe into the ergosphere. This probe is programmed to split into two parts at a precise moment. One fragment is directed to fall into the black hole, engineered to follow a trajectory that gives it negative energy. Due to the conservation of energy, the other fragment must then recoil with more energy than the original probe had when it entered. This second piece escapes the ergosphere, carrying away with it a portion of the black hole's rotational energy. It's a form of cosmic energy laundering, where the black hole's spin is converted into usable power, causing the black hole to slow down ever so slightly in the process. The implications of mastering such a technology are staggering. A civilization that could harness the Penrose process would have access to an energy source dwarfing the output of every star in a galaxy. This isn't just about powering cities. It's about achieving the energy densities necessary to manipulate the fabric of spacetime on a fundamental level. And this brings us to the heart of how the ergosphere could be the key to unlocking the Kerr black hole's potential as a time machine. The ring singularity at the center is a gateway, but it is also notoriously unstable. The very forces that created the intense, focused gravity of a rapidly spinning mass also threaten to collapse any tunnel through it the instant it forms. To stabilize a passage through the ring, to prop it open long enough for a vessel to pass, would require a counteracting force of unbelievable magnitude, a form of negative energy or some other exotic physics to keep the throat of the wormhole from pinching shut. This is where the mastery of the ergosphere becomes essential. the ability to extract and manipulate energy on the scale of the Penrose process might be the prerequisite for generating the stability field needed for a safe transit. A sufficiently advanced society could learn to use the ergosphere's own intense frame-dragging effects to their advantage. By carefully injecting energy or manipulating fields within this region, they might be able to create a resonant effect that echoes inward, calming the violent turbulence around the ring singularity and reinforcing the structure of the closed time-like curve. It would be the ultimate feat of cosmic engineering, not unlike building a stabilizing gyroscope inside a hurricane. The ergosphere, therefore, transforms from a simple source of power into a control panel for the black hole's internal geometry. Taming the ergosphere could be the final, critical step in converting a wild, natural phenomenon into a navigable time portal, the first successful passage through a stabilized Kerr black hole gateway would represent a watershed moment in the history of the cosmos, an event far more significant than the invention of the wheel or the discovery of fire. It would mark the true dawn of time travel as a practical reality. The civilization that achieved this would instantly transcend the linear prison of the present moment. Their domain would no longer be limited to the vastness of space, but would extend across the eons. This achievement would not be a one-time stunt. It would open up an entire new field of temporal engineering. Once the principle was proven, they could seek out other Kerr black holes, mapping the temporal connections each one offered, potentially creating a network of gateways linking different eras. They could establish outposts in the deep past to observe the formation of the first stars, or travel to the far future to witness the fate of the universe. This vision also provides a compelling and perhaps sobering answer to the question of why we haven't encountered obvious time travelers. A civilization that has reached this level of mastery would have an understanding of causality and paradox that is utterly beyond our own. Their first rule of temporal engagement would likely be one of non-interference, a prime directive enforced not by law, but by the cold, hard logic of the Novikov self-consistency principle. Their expeditions into the past would be exercises in supreme subtlety, designed to observe without altering, to learn without leaving a trace. Their presence would be ghost-like, integrated so perfectly into the flow of events that their actions would be indistinguishable from chance. The very stability of our timeline could be the best evidence that such travelers exist, and that they are consummate professionals, ensuring that the history that led to their own existence remains perfectly, elegantly intact. But what if the keys to time travel are not hidden in the laws of physics, but in the very nature of our reality? This brings us to a theory that has leapt from the pages of philosophy and science fiction into serious scientific discourse, the simulation hypothesis. It proposes a staggering possibility that our universe, with all its vastness and history, is not a fundamental reality, but an incredibly sophisticated simulation, much like a hyper-advanced video game running on a computer of cosmic proportions. In this context, our relentless search for wormholes and cosmic strings might be missing the point entirely, because time travel would not be a physical process, but a software function. Think about any modern video game or virtual world. As a player or a developer, how do you manipulate time? You don't build a complex machine within the game world. Instead, you interact with the system running the simulation. You load a previous save file, effectively rewinding the entire virtual world to an earlier state. Or you might access the game's code and database to review past events, watching them play out without altering the current timeline. From the perspective of a character inside the simulation, this would be the ultimate form of time travel, a complete and instantaneous reversal or review of history, with no need for exotic matter or spinning black holes. The laws of physics within the simulation would be completely bypassed by commands from a higher level of reality. If our cosmos is such a simulation, then the universe's first instance of time travel would have a very clear definition. It would be the moment the beings running this simulation, the programmers or simulators, first decided to rewind the cosmic clock or run a historical query. Perhaps it was for debugging purposes. An anomaly in the early universe required them to roll back to a point just after the Big Bang and try again. Or maybe it was for academic study, a civilization of hyper-intelligent beings running a cosmological experiment might periodically pause, rewind, and observe specific eras in finer detail. This act would be the true primordial time travel event, happening outside our space-time continuum, but having profound effects within it. The consistent laws of physics we observe could be the result of many such iterations and refinements, until the simulators settled on a stable, interesting version of the simulation. This idea also opens up a second, even more thrilling possibility for what the first time travel could be. What if the simulation itself gave rise to a form of consciousness that eventually became aware of its own programmed nature? The first time travel event from within the simulation would occur when a complex program, an advanced artificial intelligence, or perhaps even a biological civilization like our own, somehow managed to hack the source code. This wouldn't involve rockets or reactors, but a deep understanding of the mathematical and informational underpinnings of reality. By discovering a backdoor or a vulnerability in the simulation's architecture, such an entity could gain read or write access to the universal database. They could, in effect, become players with admin privileges, able to review past events or, if given right access, alter them. This would be the ultimate scientific and technological achievement for any civilization, not just understanding the laws of nature, but learning to rewrite them. The simulation hypothesis offers a powerful, albeit speculative, solution to many of the paradoxes that plague other time travel theories. The grandfather paradox, for example, becomes a simple issue of data management. If you change the past within the simulation, you are not creating a logical inconsistency in a single timeline. You are either creating a new branch of the simulation, a forked save file, or you are simply editing the saved data. The simulator's computer would handle the processing required to make the new timeline consistent. Our perception of a single, unchangeable past might just be a feature of the simulation's user interface, designed to make the experience coherent for the simulated consciousnesses within it. Furthermore, the bizarre findings of quantum mechanics, like the role of the observer in collapsing probabilities, could be explained as optimizations to save on processing power, only rendering the fine details of reality when someone is looking. While the idea that we are living in a simulation can feel like modern mythology, it is grounded in a logical progression of our own technological capabilities. We are already creating increasingly realistic virtual worlds. If our civilization continues to advance, it's conceivable that we might one day run simulations of such complexity that they contain conscious beings who believe their world is real. If we can do that, then it is statistically probable that a more advanced civilization in the base reality has already done so, and that we are inside one of their countless simulations. This line of reasoning makes the hypothesis difficult to dismiss outright. When we gaze at the night sky, we may not be looking at a physical cosmos, but at the breathtaking graphics of a simulation whose true purpose we can only guess at. The first time travel was therefore not an event in our history, but a function in the code that defines our existence, a capability that has been there all along, waiting for us to discover the cheat codes to reality itself. But if our reality is a simulation, where are the telltale signs? Where is the cosmic glitch in the matrix that betrays the underlying code? Proponents of the hypothesis point to several intriguing, albeit highly speculative, clues embedded in the fabric of our universe. One of the most compelling is the apparent fine-tuning of the fundamental constants of nature. Think of these constants as the initial settings in a computer program. The gravitational constant, the strength of the electromagnetic force, the mass of an electron. These values seem arbitrarily chosen, yet if any of them were altered by even a minuscule amount, the universe as we know it would not exist. There would be no stars, no planets, no chemistry, and certainly no life. This precise calibration has led some to wonder if these constants aren't the product of random chance, but rather carefully selected parameters, like lines of code written by a programmer to ensure the simulation produces interesting and complex results. There are the necessary settings for a universe that can eventually generate conscious observers who might one day question their own reality. Another potential source of evidence lies in the bizarre world of quantum mechanics. The famous double-slit experiment, where particles seem to behave as both waves and particles, and where the act of observation itself appears to collapse their wave function, has long baffled scientists. From a simulation perspective, this quantum weirdness makes perfect sense as an optimization technique, rendering a full, detailed reality for every single particle at every moment would require unimaginable computational power. Instead, a clever simulation might only render the fine details of a system when it is being observed, much like a video game only loads the high-resolution textures for the parts of the environment the player is currently looking at. The fuzzy, probabilistic nature of quantum particles could be a way of saving processing cycles, only resolving into a definite state when absolutely necessary. The speed of light, then, could be seen not as a fundamental speed limit of the cosmos, but as the processing speed limit of the cosmic computer, the maximum rate at which information can be updated across the simulation. If the first-time travel event was performed by the simulators, a deliberate rewinding or editing of the cosmic timeline, could we possibly find artifacts of that primordial intervention? The most promising place to look would be the universe's oldest and most fundamental fossil, the cosmic microwave background radiation. This afterglow of the Big Bang is a snapshot of the infant universe, and any manipulation of the initial conditions would likely have left an imprint here. Scientists meticulously analyze the CMB for any statistical anomalies, unexpected patterns, asymmetries, or correlations that defy the standard model of cosmology. While most observed anomalies have prosaic explanations or are within the margin of error, the simulation hypothesis offers a tantalizing alternative. A strange, circular cold spot in the CMB, for instance, could be interpreted not as a random fluctuation, but as a seam in the simulation, a remnant of where two different runs of the cosmic program were stitched together after a reset. Unexplained correlations between distant parts of the sky that should never have been in causal contact could be the ghostly signature of a simulator accessing and modifying multiple parts of the database simultaneously. Beyond cosmology, we could search for edits closer to home, within our own planetary history. The fossil record is not perfectly complete. It is punctuated by sudden mass extinctions and rapid bursts of evolutionary innovation. While science has provided evidence-based explanations for events like the asteroid impact that wiped out the dinosaurs, the simulation hypothesis allows for a more radical interpretation. What if some of these abrupt transitions are not natural disasters, but deliberate edits by the simulators? A sudden, unexplained change in the geological strata, or a fossil that appears impossibly out of sequence, could be seen as a patch or an update to the simulation's biological assets. Perhaps the simulators were testing different parameters for life, or maybe they found a previous evolutionary path unsatisfactory and decided to run a new experiment. The very fact that life on Earth seems to have arisen relatively quickly once conditions were right could be read as a sign of a universe pre-programmed for biogenesis, a default setting turned on to ensure the simulation would eventually produce sentient users. This line of thinking leads to a profound and slightly unsettling possibility. If we are in a simulation, then our entire quest to understand the universe through science is not an exploration of fundamental reality, but a process of reverse engineering the simulator's code. Every physical law we discover is not a law of nature, but a rule set by the programmers. The goal of physics, then, transforms from understanding the mind of God to debugging the software of the architects. Finding a unified theory of everything would be equivalent to discovering the ultimate programming language in which the simulation is written. And the first time travel event, it would be the moment we, as simulated beings, successfully hack the system, gaining not the ability to travel in time within the simulation, but the far greater power to access the source code itself, to see the history of all save files and edits, and to finally meet the beings who have been running our reality since the very first line of code was executed. But what if time travel isn't about building a colossal machine or finding a cosmic loophole, but is instead a property inherent to a certain type of particle? This leads us to a concept that emerges directly from the elegant equations of Einstein's theory of relativity, yet defies our everyday experience so profoundly that it remains one of the most intriguing what-ifs in all of physics. We are talking about tachyons, hypothetical particles that live their entire existence in a realm beyond the speed of light. The name itself comes from the Greek word tachys, meaning swift, and these entities would be the ultimate speedsters of the cosmos. According to the principles of special relativity, as an object with mass approaches the speed of light, its energy requirements become infinite, making light speed an unbreakable barrier for any ordinary matter. Tachyons, however, would turn this idea on its head. They are conceived as particles that could never travel slower than light. Their entire existence would be spent at superluminal velocities, making the light speed barrier a floor for them, not a ceiling. The most mind-bending consequence of this proposed nature involves time. Einstein's theory reveals that as velocity increases, time dilation occurs, time slows down for the moving object relative to a stationary observer. As an object approaches the speed of light, from our perspective, its clock would appear to grind to a near halt. Now, if we mathematically extend this principle to velocities beyond light speed, the equations yield a startling result. The time dilation factor becomes an imaginary number. While this sounds like pure mathematics, one physical interpretation is that for a tachyon, the arrow of time would be reversed. From our point of view, a tachyon would experience time flowing backwards. Its creation in our future would be its annihilation in its past, and its journey through space would also be a journey backwards through time. This leads to a radical and beautifully simple theory for the universe's first time travel event. It wouldn't require wormholes or cosmic strings. It would be a fundamental process woven into the fabric of particle physics. The first instance of time travel could have been the moment the very first tachyon was created. Imagine a colossal astronomical event in the far future, the collision of two neutron stars, or the evaporation of a supermassive black hole. In the tremendous energy of this cataclysm, a tachyon is born. From the moment of its creation, it streaks across the cosmos, not just through space, but backwards along the timeline. It carries with it a tiny packet of information, perhaps encoded in its quantum state, from that future event. Billions of years earlier, this tachyon arrives in the early, hot universe and interacts with the primordial soup of particles. That interaction, a whisper from the future, could have had a minuscule but crucial influence, perhaps tipping the scales in a quantum fluctuation that led to the formation of a galaxy, or setting a parameter that made the universe more hospitable for life. In this view, the first time travel was a cosmic seed, planted by the universe's future into its own past. However, the vast majority of physicists viewed tachyons with deep skepticism, and for compelling reasons rooted in the fundamental principle of causality, the idea that cause must always precede effect. Tachyons present a direct threat to this foundational concept. If you can send a message using a tachyon, you could create a situation where an effect happens before its cause, leading to logical paradoxes that physics seems determined to avoid. For instance, imagine you build a tachyon detector that is programmed to destroy its own power source the moment it receives a signal. Now, suppose you also have a tachyon emitter. You decide to send a tachyon signal to your detector 1 hour from now, but as soon as you make that decision, the detector, receiving the signal from its future, immediately destroys its power source. Now, you can no longer send the signal 1 hour from now, but if you don't send the signal, then the detector never received it, so it wouldn't have destroyed the power source, meaning you could send the signal. This is a classic causality-violating loop that creates an irresolvable logical inconsistency. The theoretical problems run even deeper. In many quantum field theory models, the existence of tachyons is associated with an instability in the vacuum. A tachyon field would imply that our current understanding of empty space is not the true lowest energy state of the universe, but rather an unstable configuration, like a pencil balanced on its tip. The slightest perturbation could cause the entire cosmos to undergo a catastrophic phase transition into a new state with completely different physical laws, a process that would be unimaginably destructive. The fact that our universe has persisted for billions of years in a stable form is strong indirect evidence that such unstable tachyon fields do not exist. Furthermore, if tachyons were real and could interact with ordinary matter, even weakly, we would expect to see their signature in high-energy particle collisions or in cosmic ray events. Decades of searching with increasingly sensitive equipment have yielded no confirmed detections. The silence of the detectors suggests that if tachyons are out there, they either do not interact with our world in any measurable way, or they simply are not there at all. Yet, the idea persists on the fringes of physics because it is such a natural, if disruptive, consequence of extending our most successful theories. Some researchers have explored ways to have tachyons without violating causality, often by proposing that they are incapable of carrying usable information, much like the entangled particles we discussed earlier. Others suggest they might be confined to extra dimensions or other realms permanently disconnected from our own. Ultimately, the tachyon remains a powerful thought experiment, a ghost in the machine of relativity that forces us to confront the absolute centrality of causality in our understanding of reality. It demonstrates that the universe's apparent prohibition on time travel might not be a limitation of engineering, but a fundamental feature of logical consistency, a rule so deeply embedded in the cosmos that even hypothetical particles are not allowed to break it. While we often picture the universe as a vast, static stage upon which galaxies drift apart, one of the most brilliant minds of the 20th century discovered that if the cosmos itself were set into motion, the very nature of time would unravel. The mathematician Kurt Gödel, a close friend and colleague of Albert Einstein at the Institute for Advanced Study, found a fascinating and deeply unsettling solution to Einstein's own field equations of general relativity. His model described a universe that is not expanding, but uniformly rotating. In a Gödel universe, everything is spinning the galaxies. The dust, the very fabric of spacetime itself, is in a state of smooth, cosmic rotation. This isn't like a galaxy spinning on its axis. It's the entire cosmos turning as a single, coherent entity. Gödel wasn't trying to describe our actual universe. He was exploring the mathematical possibilities within Einstein's theory, and in doing so, he stumbled upon a feature that Einstein himself found deeply troubling. the potential for time travel without any need for wormholes or black holes. The mechanism for this temporal looping is a direct consequence of the universal rotation. In our everyday experience, we think of time as a straight line from past to future. But in a rotating Gödel universe, the frame-dragging effect we discussed with spinning black holes is applied to the entire cosmos. The spinning motion of the universe would twist the fabric of spacetime into such a helix that certain paths through space would also become loops in time. These are, once again, closed time-like curves. Gödel demonstrated that if you were to set off on a sufficiently long and precise rocket journey in such a universe, following a great circular path that takes advantage of this twisted geometry, you could eventually return to your exact starting point in space, but you would also arrive at a moment before you even left. You would have traveled into your own past simply by navigating the large-scale structure of a spinning reality. This was a devastatingly elegant proof that time travel was not just science fiction, but a mathematically consistent possibility within the laws of physics as we understand them. Now, the obvious question is our universe a Gödel universe? All observational evidence points to no. Our cosmos is clearly expanding, not static and rotating as Gödel's model required. Measurements of the cosmic microwave background show an incredible uniformity, with no detectable sign of an overall universal rotation. If the entire universe were spinning, we would expect to see a preferred axis, a kind of cosmic North Pole, and our observations reveal no such thing. Einstein was reportedly disturbed by Gödel's finding because it implied that his theory of relativity, which he believed should enforce a clear distinction between past and future, actually permitted the very paradoxes he sought to avoid. The existence of the Gödel solution meant that time travel was not a bug in the software of general relativity, but a hidden and deeply strange feature. This leads to a compelling variation on the idea, one that brings us back to the universe's infancy. While our mature, expanded universe shows no signs of overall rotation, its earliest moments were a different story. The primordial cosmos was a seething, chaotic plasma, a medium where local regions could have been turbulent and dynamic. It is not at all far-fetched to propose that in the first fleeting instance after the Big Bang, before inflation had smoothed everything out, our universe might have possessed a slight, net rotational component. This wouldn't have been the smooth, uniform rotation of Gödel's idealized model, but a more messy and transient spin. In such an environment, the conditions necessary for closed time-like curves could have briefly flickered into existence. Microscopic time loops might have formed in the turbulent swirls of the primordial fireball, allowing quantum information to travel back tiny intervals of time. These temporary CTCs would have been incredibly short-lived as the universe underwent its rapid inflationary expansion and then continued to cool. Any net rotation would have been dramatically diluted, just as a figure skater slows their spin when they extend their arms. The twisting of spacetime would have relaxed, and the pathways that allowed for time loops would have vanished, but during that critical window, they could have played a vital role. This chaotic, rotating early universe could have used these brief causal loops to self-tune. Information about the state of the universe, a fraction of a second after the Big Bang, could have been sent back to an even earlier moment, influencing the quantum fluctuations that eventually seeded all the large-scale structure we see today. The stunning uniformity and specific properties of our cosmos might not be an accident, but the result of a feedback process that occurred when the universe was still a spinning, time travel-enabled fluid. In this view, the first time travel events were not journeys taken by anyone, but a fundamental mechanism of cosmic self-organization, a process that used the fleeting possibility of backward causation to ensure its own stable and fruitful future. Yet perhaps the most profound connection between dark energy and time lies not in future engineering, but in the ultimate fate of the cosmos. The relentless acceleration driven by dark energy points toward a possible future known as the heat death or big freeze, where the universe expands so much that galaxies, stars, and even atoms are torn apart, leaving a cold, dark, and empty void. In this distant epoch, the concept of time itself may begin to lose all meaning. With no coherent structures left to measure change, the arrow of time, which is intrinsically linked to the increase of disorder, could effectively cease to exist. From the perspective of a universe where time has no direction, every moment could be accessible simultaneously. This suggests a staggering possibility. The final act of the cosmos might not be an end, but a transformation into a state where time travel is not an action, but the fundamental condition of existence. The first true time travel event, then, could be a passive phenomenon, occurring naturally when the universe enters its final, timeless phase. A civilization desperate to escape this cosmic extinction might see the manipulation of dark energy not just as a way to control expansion, but as the only means to catalyze this transition prematurely, to transform the universe into a static, four-dimensional block where all of history is eternally present and accessible. In this radical view, dark energy is not just a key to a time machine, it is the catalyst that could unlock the universe's final form, turning the entire cosmos into a timeless archive where the first and last moments are forever connected. But to truly understand the very first moments, the domain where time travel might have been not just possible, but fundamental, we must confront the greatest unsolved problem in all of physics. For over a century, we've lived with a cosmic schism. On one hand, we have Einstein's general relativity, which paints a beautiful, classical picture of gravity as the curvature of a smooth, continuous spacetime. It masterfully describes the dance of planets, the bending of light around stars, and the warped geometry of black holes. On the other hand, we have quantum mechanics, which governs the bizarre, probabilistic world of the very small atoms, photons, and quarks. This theory is spectacularly successful in its own domain. The problem is that these two pillars of modern physics are utterly incompatible. They speak different mathematical languages and make contradictory predictions when pushed to the extremes, where gravity is incredibly strong and matter is incredibly small, such as at the center of a black hole or the very instant of the Big Bang. This is the quest for a theory of quantum gravity, the holy grail of theoretical physics. It's the attempt to find a single, unified framework that describes how gravity works when spacetime itself is no longer smooth, but becomes a seething, chaotic foam at the smallest possible scale, the Planck length. We need this theory to answer the most profound questions. What really happened at the singularity of the Big Bang? What is the final fate of information that falls into a black hole? And most tantalizingly for our journey, what is the true nature of time in these extreme regimes? Our current understanding of time travel, based on general relativity alone, is like trying to understand the inner workings of a modern computer processor using only the principles of 19th century steam engines. It gives us a rough, classical picture, but it completely misses the quantum reality that underpins everything. Now, let's theorize what such a complete theory might reveal. The most promising candidates, like string theory or loop quantum gravity, suggest that at the most fundamental level, the fabric of spacetime is not continuous. It's granular, woven from discrete, indivisible units, tiny loops, or vibrating strings. In this quantum realm, the familiar, linear flow of time we experience shatters. The concepts of before and after become fuzzy, much like the position and momentum of an electron are fuzzy in quantum mechanics. Time, in essence, becomes a quantum variable itself, subject to fluctuations and superpositions. Imagine a particle that isn't just in two places at once, but exists in a state of being at two different times at once. This is the kind of non-linear, non-intuitive reality that a theory of quantum gravity would describe. This leads us to a breathtaking possibility for the first time travel. It wouldn't be an event that happened in time. It would be an inherent, foundational property of the universe's very architecture. The bridge between the quantum and gravitational realms would be a bridge where causality itself is born from a more primitive, a causal state. In this view, the smooth, arrow-like time we experience today is an emergent phenomenon, a large-scale average that arises from countless tiny, random quantum fluctuations in the background spacetime. It's like the smooth surface of a lake emerging from the chaotic jostling of trillions of water molecules. But just as a lake's surface can be disturbed by a stone to create ripples that move backwards, the smooth flow of time could be disrupted by the intense gravity of the early universe to create temporary loops or reversals. So, what would this look like in practice? Picture the universe in the first fraction of a second of its life, compressed into a volume smaller than an atom. At this scale, the quantum nature of gravity would have been dominant. Spacetime wouldn't have been a calm, expanding balloon. It would have been a violent, frothing sea of virtual wormholes and baby universes bubbling in and out of existence. In this primordial quantum foam, the distinction between past, present, and future would have been meaningless. A fluctuation here could influence a fluctuation there, not through a signal traveling forward in time, but through a quantum connection that transcends our linear causality. The universe could have been a single, massively entangled system, where every point was connected to every other point, not just in space, but in time as well. Within this chaotic foam, the first time travel events would have been constant and microscopic. Particles, or rather the precursors to particles, would have taken brief journeys along closed time-like curves that were natural features of the quantum gravitational landscape. These wouldn't be journeys undertaken by a conscious being. They would be as natural and commonplace as radioactive decay is in our world. This causal interplay could have been the mechanism that smoothed out the infant universe, allowing information to be shared across regions that were causally disconnected according to classical physics. The stunning uniformity of the cosmic microwave background might be the direct result of the universe using these primitive time loops to talk to itself, achieving a state of thermal equilibrium, not by waiting for light to travel, but by exploiting its own quantum gravitational interconnectedness. Therefore, the search for the first time traveler becomes a search for the origin of time itself. In a universe governed by quantum gravity, the first instance of time travel wasn't a singular historical event. It was the moment, or rather, the timeless process by which linear time, as we know it, crystallized out of a more fundamental, timeless quantum reality. The universe didn't experience its first time travel. It was time travel in its earliest, most pure form. Unlocking this mystery won't just tell us how to build a time machine. It will reveal why we perceive a flowing present at all, answering the deepest question of why there is something called time, rather than nothing. Now we shift our perspective from the cosmos to the mind itself. After exploring black holes, quantum fields, and cosmic strings, we arrive at a theory that is perhaps the most intimate and yet the most profound of all. This idea suggests that the ultimate key to time travel has been with us all along, not in the distant reaches of space, but within the very nature of our own awareness. This is the consciousness-centric theory, which proposes that time is not a fundamental property of the universe, but rather a construct of consciousness. Think about your own experience of time. When you're bored, a minute can feel like an hour. When you're fully engaged in a thrilling activity, hours can feel like minutes. This fluidity hints that our perception of time's flow is deeply tied to our mental state. The theory takes this everyday observation to its logical extreme, arguing that the steady tick-tock of the clock is a powerful illusion generated by our brains to make sense of a world of change. Without a conscious observer to string events together into a narrative of cause and effect, the universe might simply be a collection of timeless, static moments. If this is true, then time travel is not about building a machine to propel a physical body through the centuries. Instead, it becomes an inner journey, a mental or spiritual achievement. The vehicle for this journey is not a contraption of metal and wires, but the cultivated focus of a trained mind. The first instance of time travel, then, would not be marked by a technological breakthrough, but by a moment of profound awakening. It would have occurred when the first conscious being in the universe, whether on Earth or on a world orbiting a long-dead star, achieved a state of enlightenment or expanded awareness that allowed it to perceive existence outside the linear stream of past, present, and future. For that being, the illusion of sequential time would have fallen away, revealing a reality where all moments coexist with equal reality. What would such a perception be like? It is nearly impossible for our linearly wired brains to comprehend, but we can use an analogy. Imagine your entire life as a vast, intricate tapestry. From your normal perspective, you can only see the single thread you are currently weaving. You remember the threads you've already laid down behind you, and you anticipate the threads you will add in the future. But an enlightened consciousness would be able to see the entire tapestry at once. Every event from your birth to your death would be simultaneously present, like landmarks on a map. This wouldn't be like watching a fast-forwarded movie of your life. It would be a mode of perception where the concepts of before and after simply lose their meaning. The being would not travel to the past. It would simply direct its attention to it, as easily as we turn our head to look at something in another part of a room. This idea finds echoes in various mystical and philosophical traditions across human history. Many contemplative practices, from deep meditation to certain psychedelic experiences, aim to quiet the chattering mind that constantly labels experience as past, present, or future. Practitioners often report states of timelessness, a feeling of being immersed in an eternal now where the usual distinctions collapse. While these are subjective experiences, the consciousness-centric theory suggests they might be glimpses of a more fundamental reality, brief moments when the filter of linear perception is lifted. The first-time traveler, then, would be the first being to stabilize this state permanently, to achieve a level of awareness where the entire timeline of their existence, and perhaps even the cosmos, became an open book. This perspective offers a radical and elegant solution to the paradoxes that plague physical time travel. The grandfather paradox simply cannot occur if time travel is a shift in perception. You cannot go back and change an event that you perceive as already complete and integral to the whole tapestry. Your journey is one of witnessing, not of altering. Your awareness expands to encompass the fact that your grandfather's life, his meeting with your grandmother, and your own birth are all fixed points in a coherent, unchanging structure. This aligns perfectly with the block universe model we discussed earlier, but it adds a crucial ingredient, a consciousness capable of navigating that block. The laws of physics don't need to prevent paradoxes, because a consciousness that sees the whole picture would have no desire to create one. It would understand the profound interconnectedness of all events. The implications for the fine-tuning of the universe are also transformed. Instead of looking for a physical mechanism like a bootstrap paradox or a message from the future, this theory suggests that the universe is structured to eventually give rise to consciousness, because consciousness is the ultimate purpose. The long cosmic evolution of galaxies, stars, and planets is not a random accident, but a necessary process to create a complex enough system, a brain or its equivalent, that can serve as a vessel for timeless awareness. The universe's constants are fine-tuned for life, because life is the gateway through which the cosmos becomes aware of itself. and in doing so, transcends the very dimension of time that it seemed to be bound by. The first time travel event was therefore the moment the universe, through its first enlightened being, woke up to its own true, timeless nature. This wasn't an anomaly. It was the cosmos achieving one of its fundamental potentialities. And so we arrive at the final, and perhaps most mind-bending, theory of all, a concept that doesn't just add another mechanism to our list, but instead reinterprets the entire cosmos through a new lens. Theory 30 proposes a staggering possibility. The first time travel event has not only already happened, but it was so flawless, so perfectly executed, that its signature is invisible to us because it is woven into the very fabric of everything we consider normal. In this view, our search for evidence has been looking for the wrong thing. We've been searching for an anomaly, a glitch in the matrix, a clock running backward. But what if the evidence isn't a strange artifact or a historical inconsistency? What if the evidence is reality itself, the consistent, reliable laws of physics that we take for granted, the reason an apple falls from a tree, the certainty that light travels at a constant speed, the very arrow of time pointing from past to future? These are not the pre-existing rules that time travel must break. Instead, they could be the direct, elegant consequence of that first, primordial journey. Think of it like this. Imagine a brilliant author writing a novel. The story has a clear beginning, a logical progression of events, and a satisfying ending. The characters act in consistent ways, and the plot is free of contradictions. Now, imagine that the author achieved this seamless narrative by writing the final chapter first, then going back to the beginning to ensure every single event in the early chapters perfectly set up that finale. From within the story, the characters would never know this happened. Their history would feel organic and unmanipulated, but the stunning coherence of their world would be the direct result of that authorial time travel. This is the essence of this final theory. Our universe is that perfectly crafted novel. The author could have been a future intelligence, the universe itself in a state of cosmic consciousness, or even a self-consistent loop of cause and effect that bootstrapped existence into being. Their intervention, their journey back to the beginning, was so masterful that it left no messy fingerprints, only a perfectly self-consistent timeline. This idea offers a powerful, almost poetic, resolution to the puzzle of cosmic fine-tuning. Why do the fundamental constants seem so exquisitely calibrated for complexity in life? The standard answer is either a staggering coincidence or the existence of a multiverse where we just happen to live in the lucky one. But this theory provides a third option. The constants are fine-tuned because they were tuned. That initial, paradox-free time travel event adjusted the dials at the moment of the Big Bang, setting the gravitational constant, the strength of nuclear forces, and the mass of the electron to the precise values needed for galaxies, stars, planets, and eventually, conscious observers to emerge. The universe isn't fine-tuned for life by chance. It was engineered for a future that required life to eventually understand, and perhaps even complete the loop. The fine-tuning isn't a question to be answered by cosmology alone, but the ultimate clue in a cosmic detective story, pointing directly to a foundational act of temporal engineering. This perspective also reframes the famous Fermi paradox, the question of where all the aliens are. If time travel is possible and has already been used to shape the cosmos, then advanced civilizations may not be missing from our current moment in space. They might be operating outside our linear perception of time. Their presence wouldn't be felt as spacecraft in our skies, but as a subtle, guiding hand embedded in the laws of nature. They wouldn't be tourists leaving trash in the Jurassic period. They would be architects whose work is complete and whose blueprint is reality itself. The profound silence of the cosmos, which some interpret as evidence of our solitude, could instead be the quiet hum of a perfectly calibrated machine. a universe running exactly as intended after its initial setup, was complete billions of years ago. Ultimately, this theory challenges us to reconsider the nature of evidence and discovery. The greatest secrets are not always hidden in the shadows. Sometimes they are hiding in plain sight, masquerading as normalcy. The fact that we live in a universe that is coherent, logical, and governed by mathematical laws that we can discover may be the most profound evidence that a form of cosmic reason was applied at the source. Our entire scientific endeavor, our drive to find a theory of everything, could be seen as us slowly reverse engineering the master plan put in place during that first and only necessary journey through time. We are not just studying the universe, we are deciphering the artifact of the first time traveler, an artifact so vast and so complete that it is everything we see, everything we are, and every law we have ever uncovered. The journey to find the first-time traveler ends not with a machine in a lab or a wormhole in space, but with a humbling realization. We may be living inside the perfectly preserved evidence of the universe's greatest and most secret act. And so, after this incredible voyage through 30 distinct visions of reality, we find ourselves back at the beginning, but with a perspective forever altered. We have ventured from the colossal, cyclic rebirths of the Big Bounce to the fleeting quantum whispers of entangled particles. We have grappled with the cosmic architecture of wormholes and the philosophical vertigo of the block universe, where all of time simply is. We have even dared to consider that our entire existence might be an elaborate simulation, or that the key to time travel lies not in a machine, but within the very nature of our own consciousness. This journey has been more than a catalog of strange ideas. It has been a profound challenge to some of our most deeply held assumptions about cause and effect, about the nature of existence itself. What this exploration reveals is that the search for the universe's first time traveler is not a niche puzzle for theoretical physicists. It is a fundamental human inquiry that pushes at the very boundaries of science, philosophy, and imagination. It forces us to ask what time truly is, whether our experience of a flowing present is an illusion, and if the laws of physics are absolute or merely the local bylaws of our particular cosmic neighborhood. Each theory we have examined, from the hyper-physical like Tipler's cylinder to the deeply metaphysical like the consciousness-centric view, offers a different lens through which to view reality. None may provide a definitive answer, but collectively, they map the outer frontiers of what is conceivable, reminding us that the universe is far stranger and more wonderful than we often allow ourselves to believe. This quest ultimately reframes our place in the cosmos, whether we are accidental inhabitants of a randomly fine-tuned universe, essential participants in a cosmic bootstrap paradox, or simulated minds in a grand computation. The act of asking these questions is significant. Our curiosity itself becomes a vital part of the story. By striving to understand the universe's deepest secrets, we are, in a sense, fulfilling a potential that may have been woven into the fabric of reality from its very first instant. The journey to comprehend time travel is, therefore, a journey of self-discovery, an attempt to understand not just how the universe works, but what our role within it might be. Now, this is where the conversation truly begins, and where I want to hear from you. After this whirlwind tour of possibilities, which theory captured your imagination the most? Does the elegant, self-consistent loop of the Nabokov principle feel like the most satisfying solution to the paradox problem? Or does the boundless creativity of the many worlds interpretation, with its infinite branching timelines, feel more compelling? Perhaps the sheer epic scale of the white hole cosmology, painting our Big Bang as the aftermath of another universe's death, left you in awe. Maybe the idea that our reality is a projection, a holographic illusion, resonates with you on a deeper level. There are no wrong answers here, only different doorways into the unknown. Share your thoughts and your favorite theories in the comments below. Let's continue this discussion and explore these mysteries together. What idea keeps you up at night, staring at the ceiling and wondering about the nature of it all? If you enjoyed this deep dive into the edges of understanding, make sure to subscribe and hit the notification bell. We have so many more mysteries of the universe to explore, from the enigmas of dark matter and dark energy to the search for extraterrestrial intelligence. The journey is far from over. Thank you for joining me on this expedition to the very limits of time